frequency response analysis. That is, so far we have seen in time domain analysis. Hereafter, we are going to see the control system design in frequency domain. How we will get the frequency response of the system. I think you might have done some experiment in an electronics lab. You will be given with the amplifier. You will be given amplifier. For that amplifier, you will be asked to find the frequency response. What you will do is you will give me a sinusoidal input. Sinusoidal input you will give with the constant amplitude. Constant amplitude. Input will be constant amplitude. For that, you will get the output for a linear system. Amplifier is a linear system. For a linear system, the output also a sinusoidal system, signal. Sinusoidal sine signal. Input is sine wave, output also sine wave. You will, but you are keeping the amplitude constant, but you will vary the frequency from 0 to maximum possible value. For that, for every frequency, you will measure the magnitude. You will measure the magnitude and note down. Finally, you will draw the frequency response. The frequency response you will draw. It is you will take a logarithmic scale in x-axis and decibel scale in y-axis, and you will draw the frequency response for that amplitude for different input frequencies. You will get a response like this. A trapezoidal signal like this you will get. You will be asked to find the cutoff frequency. That is 1 by √2 times of the magnitude of this magnitude. This is the ultimate or the maximum magnitude you got. From there, you will be subtracted 1 by √2 times and you find the magnitude. At that point, what is the frequency? That is called lower cutoff frequency. Similarly, you will find 1 by √2 times here. That is called upper cutoff frequency. Upper cutoff frequency. Between these two is called bandwidth. You will be asked to find the bandwidth of the amplifier. What is you noted here? As frequency decreases, the amplitude is decreasing. Similarly, as the frequency increases here, amplitude decreasing. In between, the amplitude is constant. That you can notice. So the system gives different response for different frequencies. That we are going to do here. Here, this is the transfer function. For that, you are giving a sinusoidal input as input. You are getting a sinusoidal signal as output. This is the input signal. This is the output signal. For the given frequency, here this is the amplitude is A, but here amplitude we got is B. This is called the magnitude response. Magnitude, frequency response, magnitude response. You can also notice that there is a phase shift here. Between input and output. You know that for an amplifier, the total phase shift is 180 degree. The total phase shift is 180 degree for all frequencies. Let us assume. So, what is if you give signal like this as input here, if it is an amplifier, you will get a phase shift like this, 180 degree phase shift. If you draw the response for this phase shift, if you measure for different frequency, what is the phase shift if you measure? And if you draw the response, then it is called phase response. But in the lab, you did only magnitude response. We see the difference between input and output signal. Not only there is a change in amplitude, but also there is a phase shift. The signal starts here, but the signal
starts here. It means what? There is a phase shift. There is a phase shift because of it is passing through this G of S. There is a phase shift phi because of it is passing through this transfer function. If you record the phase shift also, then you can plot another response that is called phase response. That is called phase response. Phase response. That is also between log F versus phase shift. Suppose this phase shift is constant. Always there is a 90-degree phase shift. Lag phase shift means you can draw a horizontal line minus 90 degree. It means there is a constant phase shift. Constant phase shift. Always there is a delay in 90 degree. That way you can say. Suppose always there is a phase shift of plus 90 degree means that is also a horizontal line. Suppose the phase shift is changing means you will get inclined line. That is called phase response. So there are two responses, frequency responses. How we have to obtain? The input signal is sinusoidal signal. Input signal is sinusoidal, sine wave with variable frequency, different frequency. For each frequency, we measure the magnitude, we plot, that is called magnitude response or magnitude plot. Another one is called phase plot. Another one is called phase plot. What is the phase difference between input and output? We know that for a transistor, what is the phase shift? Suppose you are giving an input signal here. What is the phase shift for a transistor? There is a delay in 90 degree. So, 180 degree phase shift. 180 degree phase shift. If you give a signal like this, there is a 180 degree phase shift like this in the output. If it is common emitter amplifier, 180 degree phase shift. So that phase shift is constant for all frequencies means you will get a horizontal line like this. That is called phase response. In electronics lab, you plotted only amplitude response. You plotted only amplitude response. You didn't consider that phase response since it is constant. But here we consider both amplitude response as well as phase response. Both we will consider. What is the output? The output C of t equal to the input amplitude is A. Input amplitude is A. A multiplied by, it is, suppose you are assuming it as an amplifier of gain G means it should be multiplied by modulus of G of j omega. You are assuming that it is a gain of G. That's why it is multiplied by G of j omega. Multiplied by the signal is input also sine omega t, output also sine omega t. There is no change in frequency, but there is a, if it is a linear system, there won't be any change in frequency. That is output also sine omega t. The amplitude is modified by A times G of j omega. The input signal amplitude is A, but the output signal amplitude is A times modulus of G of j omega. So amplitude is equal to B. Let us call this is equal to B. B equal to A times modulus of G of j omega multiplied by sine omega t. That's all. There is no change in frequency. But there is a phase shift. That's why that phi of omega is added to that omega t. There is a phase shift. Shift in phase. Shift in phase. That's why the output signal is B omega sine omega t plus phi of omega. Suppose if A equal to 1 means, what is B of omega? B of omega equal to modulus of G of j omega. If A equal to 1, if A equal to 1 means, A times modulus of G of j omega is nothing but G of modulus of G of j omega, because A equal to 1. What will happen to the phase angle phi of omega is because of phase shift introduced by angle of G of j omega. Angle of G of j omega. Therefore, what is the change between input and output? The magnitude is changed by B of omega times. That is modulus of G of j omega times. What is the change in phase shift angle of G of j omega? Here you notice that the phase shift added is angle of G of j omega. That's why the magnitude response is nothing but modulus of G of j omega. The magnitude response is nothing but a modulus of G of j omega, because V of omega equal to V of omega, the output amplitude equal to modulus of G of j omega when A equal to 1. Similarly, the phase angle equal to angle of G of j omega. That's why to get the frequency response, magnitude plot as well as phase plot, we are plotting modulus of J of j omega for magnitude plot and angle of J of j omega for phase plot by varying omega from 0 to infinity. By varying omega from 0 to infinity. So the magnitude plot is modulus of G of j omega by varying omega from 0 to infinity. What is omega? What is G of S? Suppose I am having a first order system, means K upon tau S plus 1. If you replace S by j omega, then it is called frequency transfer function. G of j omega equal to K upon j tau omega plus 1. J tau omega or j omega tau, like that you can write. Or you can write K upon j omega tau plus 1. This is called the frequency transfer function. If you vary omega, that is frequency, from 0 to infinity, you will get magnitude plot as well as phase plot. How to draw this phase plot and magnitude plot without conducting experiment? That we can do. There are methods to find frequency response. The frequency response will be looking like this. For any G of S, if you plot, it will be like this. This frequency response will be looking like this. Here, the specification, frequency domain specifications can be found from this frequency response. Time domain specifications we found in that response. This is overshoot MP. This is overshoot MP. TP. At this time, this is called TP. Raise time TR. And settling time TS. These are all we found in time domain specifications. Like that, here also we can specify some responses. At one point, the magnitude, output magnitude, at particular frequency, the output magnitude will be very high. That magnitude is called MR. That magnitude is called MR. That frequency is called omega R. That MR is called resonant peak. Resonant peak MR. That frequency is called a resonant frequency omega R. At resonant frequency, the amplitude, output amplitude will be maximum. Here, as frequency increases, the amplitude go on decreases. Amplitude go on decreases. The response will be, approximate response will be like this. It go on decreases amplitude. At one particular point, the amplitude is reduced by 1 by root 2 times this value. Suppose this magnitude is 1 means at this point, the magnitude is 1 by root 2 times. 1 by root 2 times decreased. This point is called this cutoff frequency. This cutoff point, the frequency at this point is called cutoff frequency. Cutoff frequency. Here, if you tell in decibel scale, this magnitude is 3 dB. 3 dB. The amplitude is reduced by 1 by root 2 times. And it's in decibel scale, the amplitude is reduced by 3 dB. Suppose here, the amplitude is 1 means 0 dB here. That's why at this point, minus 3 dB. This point may also be called as minus 3 dB point, or cutoff point, or cutoff frequency. The frequency at which it occurs is the cutoff frequency. Here, the bandwidth, the range of frequency from 0 to at this FR is called or omega R. We can say FR or omega R. If radians means omega, hertz means F. So here, this bandwidth, this width is called bandwidth. omega r. The frequency up to which the magnitude is within the 3 dB bandwidth. That is called bandwidth. So bandwidth is omega r minus 0, that is equal to omega r. If you tell in hertz, fr minus 0 equal to fr. It is only right-sided signal, right-sided signal. There is no left side, one-sided signal. The slope at which it decreases here, the slope at which it decreases here is called cutoff rate. This point is called cutoff point. Cutoff point. At cutoff point, what is the slope? That slope is called cutoff rate. It decreases at so many dB per decade. Like that we can tell. So this is called cutoff rate. The speed at which it decreases is cutoff rate. Gain margin and phase margin I will let you later. Gain margin and phase margin we'll see later. These are all frequency domain specifications. These are all called frequency domain specifications. Let us see once again. Resonant frequency means the frequency at which the amplitude is maximum. The maximum amplitude, MR, is called resonant peak. Cutoff frequency is the frequency at which the magnitude is reduced by 1 by root 2 times, or the magnitude is reduced by 3 dB. That point is called cutoff. The frequency at which it reaches is called cutoff frequency. The distance between 0 and cutoff frequency, omega r, is called bandwidth. The bandwidth is omega r minus 0, that is equal to omega r. If we are talking in terms of hertz, then it is called fr minus 0, that is equal to fr. The slope at the cutoff point is called cutoff rate. Gain margin and phase margin are relative stability, that we will see later. I'll let you know later. The frequency plots, there are the 5 different frequency plots are there. One is linear frequency plot. In the linear frequency plot, the x-axis will be in linear scale and y will be also in linear scale. Then it is called linear plot, linear frequency plot. Another one is linear magnitude versus log plot. Here, this alone is taken in logarithmic scale, log f, but magnitude is in linear only. Semilog sheet, you will draw in semilog sheet, that is called linear magnitude versus log plot. The third one is called Bode plot, that we are going to learn. Bode plot means this is in logarithmic scale, x-axis in logarithmic scale, y-axis in decibel scale. Decibel scale. This g of j omega is taken 20 log modulus of g of j omega. If you take, that will be in decibel scale. So y-axis in decibel scale, x-axis in logarithmic scale means then it is called logarithmic plot or Bode plot. Both are in logarithmic scale. Y-axis as well as x-axis, both are in logarithmic scale. Then it is called Bode plot. The another plot is called Nyquist plot. Here, the x-axis is in frequency scale, y-axis is in magnitude. If you plot only magnitude, if you didn't consider, and this linear, all these plots, first is what? Linear frequency plot. Second one is linear magnitude versus log omega plot. Third one is Bode plot. In all these cases, we can draw both magnitude as well as phase. Both magnitude as well as phase. Two plots are there. One is magnitude plot. Another plot is called phase plot. This is called phase plot. Angle of g of j omega versus log f. Log f. This is called phase plot. This is called magnitude plot. Magnitude. Both we can plot for 1, 2, 3. The fourth plot is Nyquist plot or polar plot. In that we are not taking f on axis. Instead, we are plotting in a polar chart. Polar chart means it will be like this. Circles will be there. circles will be there like this. This is 0 degree, 90 degree, 180 degree, 270 degree, again 360 degree. So the angle will be given like this. See, 10 degree, 20 degree, like that it is given. 90 degree, 180 degree, like that. These axes will be there. So we can plot in polar way. We can represent in two coordinates. One is rectangular coordinate. Rectangular coordinate, this is this axis is real axis. This will be imaginary axis. The same can be represented in polar way, magnitude versus angle. Morning also we have seen one sum in that this pole is at a distance of 3, omega n equal to 3, and its angle is cos inverse of 0.5, that is 60 degree. So we can say 120 degree. This point can be represented as 3 angle 120. So that way we can plot between magnitude and phase. For each frequency, we know the magnitude. For each frequency, we know the phase. If you plot magnitude and phase, you will get a plot in polar chart. This chart is called polar chart. Polar chart. In the polar chart, each point you have one magnitude, one angle. Phase angle, magnitude. Phase angle, magnitude. You can combine and you can draw the plot. That is called polar plot. Suppose you are drawing a polar plot for a first order system. Polar plot for a first order system. You will get a plot like this. You will get a plot like this. This is called polar plot. For omega equal to 0, you got here. When omega equal to infinity, because we plot the frequency response from omega equal to 0 to infinity. If you vary the frequency, you will get plot like this. You will get plot like this. This is first order plot. First order system. Polar plot. Or Nyquist plot. We can call it as polar plot or Nyquist plot. If you draw the for second order system, if you draw the polar plot for second order system, 1 by s multiplied by s plus tau s plus 1. For that, if you vary omega, this is g of s. What is g of j omega? G of j omega equal to 1 upon j omega multiplied by tau j omega tau plus 1. Here, if you vary omega from 0 to infinity, if you vary omega from 0 to infinity, you will get a plot. If you substitute omega equal to 0, what you will get? Infinity. 1 by infinity. Therefore, 0. 1 by 0. Infinity. You will get infinity. Angle will be 90 degree. I will tell. We'll see all those things later. But anyhow, I'll tell you. Angle will be minus 90 degree. Magnitude will be infinity. So, if you draw the type 1, what is the type number? Type 1, second order polar plot means it comes from here and it will be like this. If you draw the type 1 third order system, it will be like this. So these are all we'll see later. How it came and all we'll draw. Actually, we'll draw. Nyquist plot we'll draw for different transfer functions. We'll see later. But if you consider a third order type 1 system, its Nyquist plot or polar plot will be looking like this. This is 0 degree. This is 90 degree. This is 180 degree. This is 270 degree or minus 90 degree. Angle will be initially minus 90 degree. That's why it comes from here. And finally it comes to 0. Because when omega equal to infinity, amplitude becomes 0. That's why finally it approaches 0. Here, if it crosses at 180, exactly at minus 1, that is marginally stable system. If it crosses after this minus 1, then it is called unstable system. Then it is called unstable system. So if it crosses 180 before -1, if it crosses 180 degree before -1, we can say that the system is stable. In root locus, how we find stable system and all? If it crosses j omega axis, we are saying that it becomes unstable. It becomes unstable. Like that here also, if we increase k, suppose here the value of k is k1, here this is k2, here it is k3. The same frequency response is plotted for different values of k. This is for k1, Nyquist plot is plotted. This is for k2, Nyquist plot is plotted. For same system. For k3, this is plotted. Here, when k equal to k max, it passing exactly through -1. When k is less than k max, it is crosses 180 before -1. Therefore, this is stable. This is marginally stable. This is unstable. Unstable, we can say. So, we can say that the system can be bring to stable state by decreasing k. Because if we decrease k, the plot will cross -1. The plot will cross 180 before -1. The plot will cross 180 before -1. So we can talk like that. In other words, if we increase this much k, it will cross -1. If we increase this much k, it will cross -1. That is called gain margin. I told you that I'll explain this later. So with this plot, I cannot explain that. If we increase k, the frequency response will be amplified. If we increase k, output magnitude will increase, That's why the plot will amplify like this. But it becomes unstable. Because it crosses 180 after -1. So by using this frequency response, we can say that this much k is required to become unstable. That is called gain margin. We'll see later about gain margin in detail. But now I can tell this way only. So gain margin means this much k is required to make the system unstable. That is called gain margin. Or I can say that, suppose at this point, what is the phase angle at this point? This is the phase angle for this, because this is the phase angle. Phase angle means the angle of g of j omega. This plot is plotted between magnitude of g of j omega versus angle of j of j omega. No frequency is considered to plot this plot. No frequency is considered. For particular frequency, what is the magnitude? What is the phase? That point is marked. Then for next frequency, what is the magnitude? What is the plot? Next frequency, what is the magnitude? What is the phase? For next frequency, what is the magnitude? What is the phase? Like that, for many frequencies, you will find all these points and it is plotted. You can notice that if k is increased, the plot is magnified. Therefore, in other words, how much gain is required to bring the system in the verge of instability? That is called gain margin. Suppose you are having the original plot is like this. It crosses -1. It crosses 180 before -1. Suppose you increase k so that it goes through this -1, means how much k is increased? K is increased by 3 times. Therefore, gain margin is 3. If I increase gain 3 times, system becomes unstable. If I want to tell this in decibel scale, 20 log 3. 20 log 3 is the gain margin in decibel scale. In linear scale, 3 is the gain margin, because suppose the present gain is 1 means when gain equal to 3, it becomes marginally stable means 3 is the gain margin. In decibel scale, 20 log 3. Initially, gain is 10. If you increase 30 gain, it becomes unstable means how much it is increased? 3 times increased. Therefore, gain margin is 3. Suppose the initial gain is 5. When it becomes 50, it becomes unstable means how much gain is increased? 10 times increased. Therefore, gain margin is 10. If we talk the 10 in logarithmic scale, decibel scale, 20 log 10 is the gain margin. So gain margin means by what factor we have to multiply the gain K so that the system becomes in the verge of instability. So the factor is 3. In the first case, gain of the system is 1. If we make the gain of the system equal to 3, it becomes unstable. Therefore, factor is 3. In the second system, the gain of the system is 10. When it becomes 30, it becomes unstable. Gain of the system becomes 30, it becomes unstable. Factor is 3. If you multiply by 3, it becomes unstable. Therefore, gain margin is 3. The third system we have seen, initially its gain is 5. If it becomes 50, it becomes unstable. The factor is 10. If you multiply 10-fold, 10 times if you increase the gain, the factor is 10. Therefore, gain margin is 10. If we talk the gain margin in decibel scale, 20 log 3 faster for the first system. Second system also 20 log 3. Third system also, third system is 20 log 10. 20 log 10. So that is called gain margin. What is phase margin? To understand phase margin, we'll consider the same type 1 third order system. Type 1 third order system. If you increase the gain, it amplify like this. If you increase the gain, it amplify like this. So if you increase gain, it becomes unstable. I am not increasing the gain, but I am increasing the phase shift. What happens? If I increase the phase shift, what happens? For example, this is the system. The phase shift for a frequency omega 1 equal to, say, what is this angle? Up to this 90 plus 45, 135. So we can say that 135 degree at this point. If I increase this 135, I'm adding another 180 minus 135, how much? 45. If I add another 45 degree minus 45 degree to the system, I'm introducing a phase shift. I'm introducing phase shift only. I'm not changing the gain. Only introducing phase shift. Then what will happen? This point will move along this plot and comes here. Am I correct or not? Am I correct or not? This will move, comes here. So the same point will move along like this. Suppose I'm having a unit circle. I'm having a unit circle like this. I'm having a unit circle like this. This plot crosses the unit circle here. Unit circle here. This is minus j. This is plus j. This is minus 1. This is plus 1. Am I correct? Unit circle. Here, the angle is not 135. Let it be 90 plus 20. How much? 110. 110 minus 110. I am introducing a phase shift of how much? 180 I required. I am introducing, here it cuts the unit circle. Here it cuts the unit circle. Here the angle is 110. I want to make it minus 180. How much I have to add? 70. If I add 70 degree at this point, the same frequency without changing magnitude, if I add minus 70 degree, what will happen? This point will move and come here. So if I introduce phase shift also, the system becomes unstable. It becomes marginally stable. So when it crosses minus 1, the system becomes marginally stable. But I am not increasing any gain, but I introduce only phase shift. Because of that phase shift, it becomes unstable. That's why the phase margin is 70 degree. The phase margin is 70 degree because it has 110. If I introduce phase shift only into that system, now I am not increasing the gain. Only phase shift is introduced, the system becomes marginally stable. That's why the system has a phase margin of 70 degree. That is called phase margin. That is called phase margin. So the gain margin and phase margin also frequency domain specifications. And now Nyquist plot means polar plot. Nyquist plot means polar plot. Nichols plot means that is also polar plot plotted on a Nichols chart. If you plot the polar chart in a Nichols chart, then it is called Nichols plot. So we are going to study about these three only: polar plot, Nyquist plot, and Nichols plot. These three, if you draw the Nyquist plot on a Nichols chart, then it is called Nichols plot. These are the three plots that we are going to see. In the previous class, we have seen introduction to frequency response analysis. Now let us see how to draw the Bode plot. Bode plot, we have seen various types of frequency responses. One of them is Bode plot. Bode plot, we can draw the approximate frequency response without conducting any experiment. Just if we know the transfer function of any system, we can find the frequency response. We know that how it is difficult to find the frequency response experimentally. So that can be easily obtained if you know the mathematical model in terms of transfer function. The Bode plot means it has two parts. One is called magnitude plot, and another one is phase plot. We know that for a system G of S, if you give sinusoidal input with variable frequency, the output also a sinusoidal frequency of variable frequency. For every frequency, what is the ratio between input and output magnitude is called magnitude plot. For varying the frequency from 0 to infinity, and we are finding the output magnitude by input magnitude. If you find the ratio of output magnitude by input magnitude, and if you plot in decibel scale, x-axis is in logarithmic scale and the y-axis in decibel scale, then it is called magnitude plot. Phase plot is for different frequencies, for varying the frequencies, what is the phase shift in the output for every frequency, you will find. If you plot that, then it is called phase plot. That is in degrees. So there are two plots. One is magnitude plot, another one is phase plot. For as frequency varies from 0 to infinity, but constant input magnitude. If you assume it as a unity, then if we have to plot the magnitude plot is modulus of G of j omega. Is nothing but magnitude plot. Modulus of G of j omega, as omega varies from 0 to infinity, is called magnitude plot. Phase plot is nothing but angle of G of j omega, as omega varies from 0 to infinity. It's called phase plot. That we are going to do for various transfer functions. Suppose I'm having a transfer function G of S equal to K upon tau S plus 1 multiplied by tau 1 S plus 1, and suppose this is the transfer function. For that, we have to draw the frequency response. Means the first step is we have to find the frequency transfer function. We have to replace S by j omega. If you replace S by j omega, what you will get? J omega tau 3 plus 1 upon j omega tau 1 plus 1. J omega tau 2 plus 1. This we will get. Replace S by j omega. You will get frequency transfer function. For that, what is magnitude? Modulus of g of j omega, we have to plot as omega varies from 0 to infinity means modulus of k is k. The modulus of this value is square root of imaginary part square plus real part square divided by square root of imaginary part square plus 1 square root of imaginary part square plus 1. So we got the magnitude. Here we have to vary omega from 0 to infinity, vary omega from 0 to infinity, and find this value and plot. That is called the magnitude plot. Phase plot is angle of g of j omega. Angle of g of j omega equal to, this is in one more point we have to consider. This is in linear scale. We are in need of logarithmic scale, decibel scale. So to convert this into decibel scale, 20 log k square root of omega square t cube square plus 1 divided by square root of omega square t1 square plus 1 square root of omega square t2 square plus 1. So log means multiplication become addition. Multiplication becomes addition. That's why it can be written as 20 log k plus 20 log square root of omega square t cube square plus 1 minus, it is in denominator. That's why minus square root of log 20 log square root of omega square t1 square plus 1 minus 20 log square root of omega square t2 square plus 1. So these are all. What is the advantage of writing like this? It is in decibel. Now it is in decibel. Earlier it is in linear scale. Now it is in decibel, dB. dB, decibel. The advantage is we can add for each factor. So if you know the plot for log k and 20 log omega square root of omega square t3 square plus 1, if you know the plot for these two, graphically we can add. Graphically we can add. In the same way, if you know the plots for each factor, we can add them graphically all together so that we will get the Bode plot. That is the advantage. How to add all these plots, that we will see later. So that is the method to find the magnitude Bode plot. It is very simple. If you know the transfer function, we have to deassemble like this. Then we have to find the plot quickly. Quickly we can draw. If you know the transfer function, quick rough plot or approximate plot we can quickly draw. The approximate plot is called Bode plot. Similarly, we can find the angle also. What is the angle of g of j omega in the present case? K, what is that? G of j omega equal to k, what is that? Omega, j omega t3 plus 1 upon j omega t1 plus 1 multiplied by j omega t2 plus 1. This is the given sinusoidal transfer function. What is the angle of k? Angle of k is imaginary part is 0. Angle means tan inverse of imaginary part by real part. Tan inverse of imaginary part is 0. Therefore, angle of k is always 0. Therefore, angle of g of j omega equal to, for k, angle 0. For this, plus tan inverse of omega t3 divided by 1. No need to write that one. Omega t3 minus, because it is in denominator, tan inverse of omega t1 minus divided by 1 real part. No need to put. So tan inverse of omega T2 divided by 1. This is the angle plot. So we have to vary the omega from 0 to infinity. We have to get different values. We can plot without doing any experiment. We can find the phase plot as well as magnitude plot. That is called Bode plot. So what we have seen here is we can find the plot for each factor separately, and then we can add all together to get the complete plot. So what is the plot for each factor that we have to see? What is the plot for each factor that we have to see? So if we do the partial fraction, any transfer function, you will get k separately. You will get any pole at origin means, that will be there. For that, we can see the plot. Then any derivative factor in the origin, multiple, any s in the numerator, for that also we can plot. Then any first order factor in the denominator, j omega t plus 1, first order factor in the denominator. Similarly, first order factor in the numerator, for that what is the plot? Apart from that, it may be a multiple repeated poles, n and p, q, p repeated poles and q repeated zeros, like that. For that we have to see. Then it may be a quadratic, that is s square plus 2 zeta omega n s plus 1. If you write this in time constant form, it will be tau square s square plus 2 zeta tau s plus omega n square. If you write this in time constant form, it will be like this: tau square s square plus 2 zeta tau s plus 1. This is in natural frequency form. This is in time constant form. Always we use time constant form. Why? Because the gain k is correct only in time constant form. That's why always we have to take k. Whenever you want to take k, means the transfer function must be in time constant form, then only the k is correct. So we used to use time constant form for all plots. Other advantages are there for Bode plot that we will see later. Time constant form. So if you write the second order transfer function in the time constant form, it may be this tau square s square plus 2 zeta tau s plus 1. It may be in the denominator or numerator. These are the fundamental factors you may obtain for a given transfer function. If you know plot for all these fundamental factors, you can draw the Bode plot. So let us see one by one how to draw the Bode plot for each factor. So first is, let us take k. Suppose g of s is equal to k, that's all. For that, what is the Bode plot? Magnitude plot is 20 log modulus of g of j omega. That is equal to, because g of j omega equal to what? G of j omega equal to k. Therefore, 20 log modulus of g of j omega equal to 20 log k. That's all. If you vary omega, k won't change. It is independent of omega. That's why for different values of k, what you will get, you have to check. If k is greater than 1, suppose k equal to 1, what you will get? 20 log 1 equal to 0 dB. If k equal to 1, if k equal to 1, if k is greater than 1, k is greater than 1, what you will get? Suppose k equal to 10, 20 log 10 equal to what? K equal to 10, 20 log 10 equal to 20 dB. You are getting, if it is k is greater than 1, if k is greater than 1, say k equal to 10, you will get a positive constant. Suppose k is less than 1, k equal to 0.1. K equal to 0.1. What you will get? 20 log 0.1. That is equal to 20 log 0.1 to the 10 to the power minus 1. 10 to the power minus 1 is nothing but 0.1. 0.1. 10 to the power minus 1 is 0.1. 1 by 10. 10 to the power minus 1 equal to 1 by 10. That is 0.1. So if you write like that, what you will get? A minus 20 log 10. That is equal to minus 20 dB. If K is 0.1, you will get minus 20 dB. K is greater than 1, let's say 10, you will get 20 dB. If K equal to 1, you will get 0 dB. What is the plot? Magnitude plot? The magnitude plot is log F. Log F. In the logarithmic scale, how you will put 0.1, 1, 10, 100, like that you will write. Am I correct? Each division is 1 decade. 1 decade. That is called 1 decade. 10 times. A fold of 10. If you multiply 0.1 by 10, you will get 1. If you multiply 1 by 10, you will get 10, like that. So fold of 10. What is the previous? Before that, what will be there? 0.01. Before that, 0.001. It never reached 0 because log 0 is undefined. Log 0 is undefined. That's why there is no x-axis value 0. So 0.01, 0.001, like that it will go. So here, usually we start with 0.1. In a special cases, we'll start with 0.01 or 0.001, like that. Usually we start with 0.1, 0.1, 1, 10, 100, like that. Here, what is the value? Y-axis in dB, x-axis in log F. Log F we marked in semilog sheet. In semilog sheet, you have to buy semilog sheet. Here, you will get 0. You will get 0. You will get 0 dB. 0 dB. That is K equal to 1. K equal to 10. K equal to 10. What you will get? Plus 20 dB. Plus 20 dB. If K equal to 0.1, you will get minus 20 dB. Minus 20 dB. When K equal to 0.1, you will get minus 20 dB. A horizontal line you will get. A horizontal line you will get. So this is the plot for K. What is the angle? Phase plot. What is the angle? Phase plot. What is the phase plot? Log F. 0.1, 1, 10, 100, like that you will get. 1 hertz, 10 hertz, 100 hertz, 0.1 hertz, like that. Phase plot is for it is only real part, no imaginary part. That's why always angle is 0. So the phase plot is 0 degree. 0 degree. Phase plot is like that. This is phase plot. Phase plot. This is magnitude plot. Magnitude plot. This is for K equal to 10, K equal to 1, K equal to 0.1. This is the magnitude plot for K equal to 10, K equal to 1, K equal to 0.1. And phase whether it is k equal to 10 or 1 or 0.1, phase plot is same. For all values of k, the phase plot is 0 only, 0 degree only. Here, how we will mark frequency will be marked as 1, 10, 100 log f. Or you can write 1 can be written as 10 power 0, 10 power 1. Sorry, 1 can be written as 10 power 0, 10 can be written as 10 power 1, 100 can be written as 10 power 2, and 0.1 can be written as 10 power minus 1. Like that also you can write. Already we have seen that what are the factors in a transfer function. K already we have seen. And S in the denominator. S in the denominator. For that, what is the Bode plot? For each factor we will see separately, then finally we will add all together. So, for that, 1 by S, G of S equal to 1 by S. For that, the sinusoidal transfer function, G of J omega equal to 1 by J omega. Or it can also be written as minus J by omega. Multiply the numerator and denominator by J, you will get minus J by omega. What is modulus of G of J omega? Equal to 1 by omega. That's all. Modulus of G of J omega, how you will find the square root of real part square, 0 square plus imaginary part square, 1 by omega square, that is equal to 1 by omega. So we got, what is the angle? Angle equal to tan inverse of imaginary part. What is imaginary part? 1 by omega, that is imaginary part. What is denominator? Real part? Real part is 0. Therefore, that is infinity. Therefore, angle of G of J omega is, angle of G of J omega is always minus 90 degree. This is minus infinity. Minus infinity, that's why always minus 90. Minus 90. So angle always minus 90. But this will vary. Magnitude plot will vary. So how to plot that? Let us plot a rough plot for 20 log decibel scale. 20 log 1 by omega. G of modulus of 20 log modulus of G of J omega equal to 20 log 1 by omega. 20 log 1 by omega, when omega equal to 1, you will get 0. When omega equal to 1, 20 log 1 by omega equal to 0. Because 20 log 1 equal to 0. Omega equal to 10, what you will get? 20 log 1 by 10. That is 20 log 0.1, that is 10 power minus 1, that is equal to minus 20 dB. Minus 20 dB. Am I correct or no? When omega equal to 10, 20 log 1 by 10, that is equal to 10 power minus 1. That minus 1 will come here. That minus 1 will come here. Any power will come as product in logarithmic scale. Therefore, minus 20 dB. You will get log 10 equal to 1. Log to the base 10 we are using. So minus 20 dB. When omega equal to 0.1, what you will get? 20 log 1 by 0.1, that is equal to 20 log 10. 1 by 0.1 equal to 10, that is equal to 20 dB. When omega equal to 0.1, it is 20 dB. When omega equal to 1, it is 0 dB. When omega equal to 10, minus 20 dB. So what is the plot? The plot is like this. The plot is like this. This is log omega. How we will mark 0.1, 1, omega equal to 0.1, 1, 10, 100, like that we will mark. So when omega equal to 1, what's its value? 0 dB. This is 0 dB. When omega equal to 1, you notice here, when omega equal to 1, 0 dB. That's why 0 dB. When omega equal to 10, minus 20 dB. Minus 20 dB. Here. So when omega equal to 10, minus 20 dB. When omega equal to 20, 0.1, it is 20 dB. 20 dB. 20 dB. When this is omega equal to 0.1, this point is omega equal to 10. This point is omega equal to 1. So what you are getting, the plot is like this. The plot is like this. What is the difference between 0.1 and 1? 0.1 and 1, 20 dB. 20 dB. Difference between the magnitude change in 0.1 to 1 is 20 dB. Again, 1 to 20, what is the change? 0 to minus 20. Again, 20 dB decreases. It decreases at the rate of 20 dB. 20 dB per decade. This width is called 1 decade. So it decreases at the rate of 20 dB minus 20 dB per decade. Like that we can write minus 20 dB per decade. Like that it decreases. So therefore, if S in the denominator, a slant line, it decreases at the rate of minus 20 dB per decade. That's all. We have to draw a horizontal, inclined line with a slope of minus 20 dB per decade. 1 decade means 0.1 to 1 is 1 decade. 1 to 10 is 1 decade. Because it is tenfold. If you multiply by 10, you will get the next. Multiply 0.1 by 10, you will get 1. If you multiply 1 by 10, you will get 10. If you multiply 10 by 10, you will get 100. Therefore, 1 decade. The slope is for 1 by S is, it decreases at the rate of minus 20 dB per decade. That's all. So what is the phase plot? Already we have seen that phase plot is because of real part is 0. Therefore, infinity we got always minus 90. Therefore, the phase plot is looking like this. If you draw the phase plot for this, this is the phase plot. Log F 1 10.1 omega equal to, this is omega equal to, or log omega, or simply you can write logarithmic scale, log omega you can write. Here it is always minus 9, always minus 9. This is the phase plot of 1 by S. This is magnitude plot of 1 by S. That's all. Suppose this is the, you see that this is omega equal to 1. Here omega equal to 0.1. Omega equal to 10. Omega equal to 100. So the magnitude, if you see, when omega equal to 1, 0. When omega equal to 10, you will get a minus 20. Minus 20. When omega equal to 0.1, plus 20. This is, the slope is minus 20 dB per decade. The phase plot, always minus 90 degree. Always minus 90 degree. Always minus 90 degree. Because real part is 0. Suppose I am having, instead of S, I am having G of S equal to 1 by S square. What you will get? G of J omega equal to what? G of J omega equal to 1 by J omega square. J omega square. What you will get? Modulus of G of J omega equal to modulus of G of J omega equal to 1 by omega square. Angle of G of j omega equal to what? Angle of G of j omega equal to 2 j omegas. For 1 j omega 90. For 2 j omegas 180 degree. So it can be written as 1 by j omega, 1 by j omega. For this one minus 90 degree, for this another minus 90 degree, therefore 180 degree. Or we can write 2 times tan inverse of imaginary part is omega, real part is 0, therefore minus, why minus in the denominator? So minus 2 times 90 degree, that is equal to minus 180 degree. The phase plot is always minus 180. If it is instead of, what is magnitude plot? 1 by omega square means 20 log modulus of G of j omega equal to 20 log 1 by omega whole square. That is equal to 40 log 1 by omega. 40 log 1 by omega. That can also be written as minus 40 log omega. Omega can be written as omega to the power minus 1. So if you bring that minus 1 as a multiplication factor, you will get minus 40 log. So when omega equal to omega equal to 1, what you will get? 0 dB. 0 dB. When omega equal to 10, when omega equal to 10, omega equal to 10, what you will get? Minus 40 dB. When omega equal to 0.1, plus 40 dB. Plus 40 dB. Because omega 0.1 equal to minus 1. So minus of minus plus, therefore 40 dB. So here, if it is 1 by s square means, what is the plot? 1 by s square means, here instead of 20, 40, here instead of minus 20, minus 40. That's all. The slope is minus 40 dB per decade. If it is 1 by s square. S cube means 3 times minus 60, 0, minus 60. Sorry, 60, 0, minus 60. Slope will be like that. So n means what? What is the, if it is instead of 2, n is there. So what you will get is 20 log modulus of G of j omega, when that is equal to 20 log n multiplied by, because G of j omega equal to 1 by j omega to the power n. So n times 20 log 1 by omega you will get. So we have to multiply. If you know 1 by omega, we can find any number. So just we have to multiply by that power. Just to multiply here, in this case, the power is 2. Therefore, 20 becomes 40. If power is 3, it becomes 60. Plus 60 minus 60. But anyhow, for omega equal to 1, always 0. Omega equal to 1, always 0. This is the plot for 1 by s. This is to know about plot. Already I told you that the distance between, this is 1, omega equal to 1. Omega equal to 1. This is omega equal to 0.1. This is omega equal to 10. Here omega equal to 100. Omega equal to 0.1. Omega equal to 1. Omega equal to 10. Omega equal to 100. What is the distance between these two? The distance between 0.1 and 1 is 1 decade. Already we have seen. 1 decade. Omega equal to 1 and omega equal to 10, the distance is called 1 decade. 1 decade. Therefore, the slope is mentioned as 20 dB. The slope here is minus 20 dB, minus 20 dB per decade. That's why in 1 decade, the magnitude decreases by 20 dB. That's why the slope is called the minus 20 dB per decade. Here in 1 decade, here the value is 1. Here the value is minus 20. You notice that? Here the value is minus 20. Here 0. But the distance between these 2 points is 1 decade. Therefore, the slope is minus 20 dB per decade. Decade means 10. So, yeah, multiplication factor of 10. That's why it is called 1 decade. Another scale is there that is called the octal. Octal. 20 dB per decade and minus 6 dB per octal. Both are same. 6 dB per octal means the frequency will be doubled. Frequency will be doubled. Here it is 0.1. Here 0.2 doubled. 0.3. This is 1. This is 0.9. Here frequency is doubled. 0.4 means here frequency is doubled. So when the frequency is doubled, during this period, the frequency is doubled. What is the decrease in amplitude? Minus 6 dB. Therefore, 20 dB per decade as well as 6 dB per octal, both are same. Sometimes they may mention minus 6 dB per octal. So you should understand that both are same. Both are same. There are 2 scales. One is octal scale and decibel scale. 1 decade means multiplication of 10 frequency. Octal means doubled, twice, doubled. So octal scale means minus 6 dB per decade. Integral factors that already we have seen. 1 by s power n means 1 by s power n means in decibel scale 20 log modulus of g of j omega equal to 1 by modulus of s power 20 log modulus of 1 by s power n. So that is equal to n times. So this can be written as 1 by s whole power n. Therefore, n times 20 log 1 by j omega to the power n. So j omega modulus of j omega to the power n that is equal to 20 log modulus of 1 by j omega to the power n. So n 20 log 1 by j omega, modulus of j omega is 1 by omega. You will get minus n 20 log omega. Therefore, you will get when omega equal to 1, 0 dB. When omega equal to 0.1, you will get plus 20. Because of 0.1, you will get another fractional number means negative. You will get another negative. Therefore, plus n 20 dB. N 20 dB. If it is 10 means, if it is omega equal to 10 means you will get minus n 20 dB. N 20 dB. If n equal to 2, what you will get? 40, 0, minus 40. N equal to 3 means 60, 0, minus 60 you will get. Bode plot at a derivative factor, 0 at the origin. That is g of s equal to s. For that, what is the Bode plot? G of j omega equal to g of j omega equal to j omega. Or it can be written as modulus of j omega equal to omega and angle equal to what? Imaginary part is omega. Real part angle equal to tan inverse of imaginary part is omega, real part is 0. Therefore, infinity. Tan inverse of omega infinity equal to tan inverse of infinity equal to 90 degree. You will get 90 degree. So angle of g of j omega always 90 degree. G of j omega equal to always 90 degree. Always 90 degree. So what will happen if omega equal to 0.1? When omega equal to 0.1, if we substitute that 20 log 0.1 equal to 1 omega equal to 0.1 means you will get 20 log 0.1 equal to 10 power minus 1 minus 20 dB. Minus 20 dB. When omega equal to 1, 20 log 1 equal to 0 dB. When omega equal to 10, what you will get? 20 log 10 equal to 20 dB. So as omega increases, it increases. Therefore, the plot is when omega equal to 0.1, omega equal to 0.1 minus 20 dB. When omega equal to 1, 0 dB. When omega equal to 10, omega equal to 10, 20 dB. So it increases. Therefore, the slope is 20 dB per decade plus positive. 20 dB per decade, positive slope. It increases per decade. What is the slope? What is the phase plot? Phase plot already we have seen always 90 degree. Therefore, phase plot is 90 degree always for 0.1, 1, 10, 100 for all. You got 90 degree always. Multiple factors. G of j omega equal to s power n. S power n. In that case, what you will get? Modulus of G of j omega equal to modulus of j omega to the power n. You will get. That is equal to, therefore, 20 log modulus of G of j omega equal to 20 log in dB scale. Modulus of j of j omega, that is omega we can put to the power n, that is equal to n 20 log omega. When omega equal to 1, you will get 0. When omega equal to 0.1, you will get minus n 20. When omega equal to 10, you will get n 20. So we have to multiply by n. Slope is positive. If s in the numerator, slope is positive. S in the denominator, slope is negative. That's all. That is the only difference. But what is the phase plot? Phase plot is j omega. Suppose n equal to 2 means j omega multiplied by j omega. For this 190 degree, for this another 90 degree, therefore 180 degree. For n equal to 2, you will get 180 degree. N equal to 3, 270 degree, like that. What is the difference here? Plus 180 degree. 1 by s means minus 90 degree. S in the numerator means G of j omega equal to j omega means plus 90 degree. G of j omega equal to 1 by j omega means minus 90 degree. That is the difference. In the phase plot, that is the difference. We have seen construction rules for Bode plot. So far, only partially we have seen. Some more construction rules are there that we'll see today. So far, we have seen how to draw Bode plot for 1 by s, s in the numerator, and k. Now, let us see how to draw Bode plot for first order factor in the denominator. That is g of s equal to 1 by tau s plus 1. For that, how to draw the Bode plot, that we'll see now. To draw Bode plot, the first step is we have to convert this into sinusoidal transfer function. Replace s by j omega. 1 by j omega tau plus 1. That is the first step. Then we have to find the magnitude. What is the magnitude? Modulus of g of j omega, that we have to find. That is equal to 1 by square root of imaginary part square plus real part square. This is magnitude plot. What is the magnitude? What is in decibel scale? That is 20 log modulus of g of j omega. That is equal to 20 log 1 by square root of omega square t square plus 1. That is equal to minus 20 log square root of omega square. For this, how to draw magnitude plot? We have to vary this omega from 0 to infinity. For that, we have to draw the magnitude plot. For that, we are considering two cases. The case one is omega tau is far, far greater than 1. Far, far greater than 1. And omega tau is far, far less than 1. Two categories. We are separating this into two cases. This equation is, for this, we have to draw the Bode plot. By varying omega from 0 to infinity, we are considering two cases. One is omega tau is far, far greater than 1. Another case is omega tau is far, far less than 1. If omega tau is far, far greater than 1, this is approximately equal to 1 is negligible. If omega tau is 1000 means 1 is negligible. Therefore, this can be written as minus 20 log square root of omega square t square. That is equal to minus 20 log omega tau. That's all. If omega tau is far, far greater than 1. Suppose omega tau is, this is for the case omega tau far, far greater than 1. That is case 1. In case 2, what we can say is omega tau is far, far less than 1. While compare with 0.001, let us assume 0.01. These are all negligible while compare with 1. That's why this can be written as minus 20 log omega tau is negligible because that is equal to 0.01 while compare with 1. Therefore, omega logs minus 20 log 1, that is equal to minus 20 log minus 20 multiplied by 0. That's why 0 dB. So omega tau is far, far greater than 1 means the equation becomes minus 20 log omega t. If omega tau is far, far less than 1 means it is equal to 0 dB. 0 dB. Only two cases. Therefore, let us assume that when omega equal to 1 by tau, what will happen? When omega equal to 1 by tau, third case, when omega tau is less than equal to 1 by tau, we can replace omega tau by 1 by t. Therefore, it becomes, the equation becomes minus 20 log omega tau square root of omega equal to 1 by tau. 1 by tau square t square plus 1. T square getting, tau square getting cancelled. Therefore, 1 plus 1, you will get 2. The third case is when omega equal to 1 by tau. When omega equal to 1 by tau, you will get the value 1. So, when omega tau is greater than 1 by tau, 1 is negligible. When omega is less than 1 by tau, when these two cases now we can define like this. When omega is greater than 1 by tau, it comes under this category. When omega is less than 1 by tau, it comes under this category. Because when omega equal to 1 by tau, it becomes 1. When omega equal to 1 by tau, it becomes 1. Therefore, when omega is greater than 1 by tau, it comes under this category. When omega is less than 1 by tau, it comes under this category. So, this omega equal to 1 by tau is the point that differentiates these two cases. When omega equal to 1 by tau, it is equal to 1. That point is called corner frequency. Omega equal to 1 by tau is called corner frequency. That point is called corner frequency. Now, let us assume that Now let us assume that G of j omega equal to 1 by square root of omega square t square plus 1. Already first case is what? When omega tau is far greater than 1 means omega square tau square is far greater than 1. That's why we can ignore 1. Therefore, G of j omega becomes 1 by square root of omega square t square, that is equal to 1 by omega tau. Therefore, 20 log modulus of G of j omega equal to 20 log 1 by omega tau, that is equal to minus 20 log omega tau. Here we are considering only the cases omega tau is far greater than 1. Therefore, 1 is negligible. We will get when omega equal to 10 by tau, what you will get? When omega equal to 10 by tau, what you will get? Substitute omega equal to 10 by tau. I said 1 by tau is the point at which it is called the Ghana frequency. We are moving away from that point. How many times? 10 times, 10 by tau. If you substitute omega equal to 10 by tau, this value equal to minus 20 log 10 by tau multiplied by tau getting cancelled. 20 log 10 equal to 1. Log 10 equal to 1, therefore minus 20 dB. Suppose omega equal to 100 by tau, what will happen? Omega equal to 100 by tau, what you will get? Then you will get minus 20 log 100 by t multiplied by t. Therefore, power 2. Therefore, you will get minus 40 dB. Minus 40 dB. What is the distance difference between when omega 1 equal to 10 by t, omega 2 equal to 100 by t, 1 decade away? What is the decrease in magnitude? 20 dB. Therefore, it decreases at the rate of, this is the 0.1. This is this is 1 by tau. This is 0.1 by tau. This is 10 by tau. This is 100 by tau. Suppose tau equal to 1, you will get conventional scale. Depends upon the tau value, you will get the scale like this. 1 by tau. What is the distance between these two? 1 decade. What is the distance? 10 times. Therefore, this is also 1 decade. Here at 1 by tau, after 1 by tau, at 10 by tau, its value is 20 dB. At 100 by tau, it is 40 dB. Therefore, it decreases at the rate of minus 20 dB per decade. It decreases at the rate of minus 20 dB per decade. Less than 1 by tau, it comes under this category. Less than 1 by tau, that is less than 1 by tau, it comes under this category. Less than 1 by tau, it comes under this category. Omega tau is negligible because it is fractional value. Less than 1 by tau means it is fractional value. Let us substitute omega is less than 1 by tau means let us put to 0.1 by t. If you put omega equal to 0.1 by t, t getting cancelled, 1 plus 0.1. 1 and 1 plus 1.1 both are almost equal. 1 and 1.1 are equal. Therefore, this can be ignored. This can be ignored when omega is less than 1 by tau. In that category, what you will get, that is left side of this point. Left side of this point, what you will get? 0, because 20 log, the magnitude is minus 20 log 1. Therefore, you will get 0 dB. Therefore, 0 dB. So, this is the plot for 1 by G of S equal to 1 by tau S plus 1. For that, this is the frequency plot. Suppose I am having like this, G of S equal to 1 by 5 S plus 1. Tau equal to what? 5. 1 by tau equal to what? 1 by tau. This implies 1 by tau equal to 1 by 5. That is equal to 0.2. Therefore, the corner frequency is 0.2. Corner frequency is 0.2 radians per second. Tau equal to 5. Corner frequency is what? 1 by tau. 1 by tau equal to 1 by 5 equal to 0.2. Therefore, corner frequency is 0.2. 1 by 2 should be labeled as 0.2. Am I correct or not? 10 by t means 10 multiplied by 0.2. That is equal to 2. 100 multiplied by 100 by t means 100 multiplied by 0.2. That is equal to 20. Am I correct or not? So the plot is like this. Up to corner frequency, it is 0. After that, it decreases at the rate of minus 20 dB per decade. Have you got? Still, you are having the confusion of 50. Corner frequency means 1 by tau. Corner frequency means omega equal to, we are assuming that omega equal to 1 by tau. At this point, 1 by tau means tau equal to 5. 1 by 5 means 0.2. Here, omega equal to 1 by 2, that is 1 by 5, that is equal to 0.2. Here, 10 by tau, that is 10 multiplied by 0.2, that is equal to 2. Here, 100 multiplied by 0.2, that is 20. Another example. G of S equal to 1 by 0.5 S plus 1. Tau equal to what? 0.5. What is the corner frequency? Corner frequency equal to 1 by 0.5. That is equal to 2. Therefore, the plot for this is here, what is that? 0.1 by t. This is what? 0.1 by t. This is 1 by t. This is what? 10 by t. This is what? 100 by t. Now 1 by t equal to 2. Therefore, this becomes 1 by t becomes 2. This point is 2 radians. This is 20 radians. This is 200 radians. 200 radians per second. This is 0.2. Like that we can mark. Because in the graph sheet, one division is what? 1 decade. So if you mark this as 0.2, this becomes 2. Therefore, up to 1 by tau, it is 0. After that, it becomes 0. After that, it becomes minus 20 dB per decade. After corner frequency, this is corner frequency. After corner frequency, it decreases like that. This is the frequency response for first order system. This is the frequency response for first order system. Suppose I am having 0.5 S plus whole square. Then what you will get? G of S, G of j omega equal to 1 by square root of 0.5 j omega plus 1. 0.5 square j omega square plus, sorry, omega square plus 1 whole square. That is equal to G of j omega equal to 1 by 0.5 square omega square plus 1. So in this case, modulus of. So if you square that, what you will get? You will get 1 by, let us assume 0.5 is tau. Generally, let us talk tau square omega square plus 1. Or what is the corner frequency? Omega equal to 1 by tau is the corner frequency. Before corner frequency, this is negligible. After corner frequency, this is negligible. Before corner frequency, tau square omega square is negligible. If you square 0.1, what you will get? 0.01. Therefore, squaring means then also it is negligible. fractional value. Therefore, before corner frequency, this is negligible. After corner frequency, this is negligible. Therefore, what you will get is 20 log modulus of G of j omega equal to 20 log 1 by, let us assume t instead of 0.2 for convenience, generalized case, t square omega square plus 1, because G of s equal to 1 by tau s plus 1 whole square. Therefore, you will get like this. This becomes minus 20 log t square omega square plus 1. When omega tau is far greater than 1, case 1, this is equal to minus 20 log t square omega square. That is equal to minus 40. If you bring that square here, minus 40 log omega tau. If second case, if omega tau is far less than 1, what you will get? Minus 20 log t square omega square is negligible. That's why 1, you will get 0 dB. So up to corner frequency 0. After that, it decreases at the rate of minus 40 dB per decade. It decreases at the rate of minus 40 dB per decade. Therefore, the plot is this is 0.1 by tau. This is 1 by tau. This is 10 by tau. This is 100 by tau. So up to 1 by tau, it is 0. After that, it decreases at the rate of minus 40 dB per decade. It decreases at the rate of minus 40 dB per decade. That's all. This is the plot for G of s equal to 1 by tau s plus 1 whole square. Suppose whole cube means it decreases at the rate of minus 60 dB per decade. Whole power n means it decreases at the rate of n multiplied by 20. Minus n multiplied by 20 dB per decade. Generalized case. Suppose now tau equal to, what we assumed, tau equal to 0.5. If you assume tau equal to 0.5, what is G of s? G of s equal to 1 upon 0.5 s plus 1 whole square. Therefore, this 1 by tau equal to 1 by 0.5 equal to what? 2. This becomes what? 0.2. This becomes what? 20. This becomes what? 200. That's all. That's all. Suppose tau equal to 10 s plus 1. 1 by tau equal to what? The corner frequency is 1 by tau equal to 1 by 10. That is equal to 0.1. Therefore, this point becomes 0.1. This is 0.01. This is, in that case, this becomes 0.1. This becomes 0.01. And this becomes 1. And this becomes 10. S plus 1 whole square. So it decreases at the rate of minus 40 dB per decade. So now we know how to draw for first order in the factor in the denominator. Suppose the first order factor is in the numerator. First order factor is G of s equal to tau s plus 1 in the numerator. What you will get? G of j omega equal to j omega plus j omega tau plus 1. Therefore, modulus of G of j omega equal to square root of omega square t square plus 1. Omega square t square plus 1. Up to corner frequency. What is corner frequency? Omega equal to 1 by tau. If you substitute omega equal to 1 by tau, it becomes 1. If corner frequency is omega 1 by tau, if omega tau is far greater than 1, it means it is on the right side of 1 by tau. Right side of 1 by tau. Omega tau is far greater than 1 means omega is far greater than 1 by tau. You understand this point now? Omega is far greater than 1 by tau. Omega tau far greater than 1 means omega is far greater than 1 by tau. So that is the category 1. In that case, 1 is negligible. You will get modulus of g of j omega equal to square root of omega square t square, that is equal to omega tau. So 20 log omega tau means 20 log omega tau means it is when omega equal to 1 by tau means 0 dB. When omega equal to 1 by tau, 20 log omega tau equal to omega equal 10 by tau, you will get 20 dB. When omega equal to 10 by tau, when 20 log omega tau equal to 40 dB, when omega equal to 100 by tau. So it increases at the rate of 40 dB per decade. It increases at the rate of 40 dB per decade. But up to corner frequency, that is second case is omega tau is far less than 1. That is omega is far less than 1 by tau. Far less than 1 by tau. Therefore, if any point is the left hand side of corner frequency, that is negligible. That is 20 log 1, that is equal to 0 dB. Any point is less than 1 by tau, it is negligible. Any point greater than 1 by tau is considerable. Consider and you have to draw. Therefore, the plot is 0.1 by tau and 1 by tau. This is 10 by tau. This is 100 by tau. Up to corner frequency 0 dB. After that, it increases at the rate of 20 dB per decade. It increases. Therefore, when g of s equal to tau s plus 1, this is the frequency response. It increases at the rate of 20 dB per decade. If suppose g of s equal to tau s plus 1 whole square, it increases at the rate of 40 dB per decade. It increase after 1 by tau, omega equal to 1 by tau, it increases at the rate of 40 dB per decade. Suppose g of s equal to tau s plus 1 whole cube, after 1 by tau, it increases at the rate of 60 dB per decade. Like that, it will increase. So, without hesitating, we can draw the frequency response for a first order system. If we know 1 by tau, that's all. If you know the time constant, that is corner frequency equal to 1 by time constant, corner frequency equal to 1 by time constant. After that, it decreases at the rate of 20 dB per decade. Before that, it is 0 dB. That is the rough plot. That is, or in other words, it is called asymptotic plot. It is called asymptotic plot. For example, I am drawing a plot for a first order system. The asymptotic plot is up to 1 by tau, it is 0. After that, it decreases at the rate of 20 dB per decade. It decreases at the rate of 20 dB per decade. What is the actual plot? This is asymptotic plot. We are ignoring omega t if it is less than omega tau is far less than 1. If it is omega tau is far greater than 1, we are ignoring 1. If we consider both, what will happen? At corner frequency, what happens? That is equal to g of j omega 20 log modulus of g of j omega equal to 20 log 1 by square root of omega square t square plus 1. That is equal to minus 20 log square root of omega square t square plus 1. That is equal to minus 20 log. If you consider both at corner frequency, omega equal to 1 by tau. If you substitute omega equal to 1 by tau, what will happen at corner frequency? This is the corner frequency. At corner frequency, I am considering both terms. This is 1 by tau square multiplied by tau square plus 1, that is equal to minus 20 log square root of 2. You will get minus 3 dB. You will get minus 3 dB. If you calculate, you will get minus 3 dB. Therefore, the frequency response, the actual plot is at this point, it decreases like this. Here, this is equal to minus 3 dB, 0 dB. Actually, up to corner frequency, we have drawn up 0 dB. But at corner frequency, there is an error of 3 dB. So, the asymptotic plot, that is the Bode plot, the difference between the Bode plot and the actual plot is, the difference between Bode plot and the exact plot is a difference of minus 3 dB only. A difference of, that too at corner frequency only. Other points it is same, asymptotic plot. This plot is called asymptotic plot. Asymptotic plot. Because it is tangent at higher and lower values of omega to the actual plot. That's why Bode plot is asymptotic plot. It has an error of minus 3 dB at corner frequency. For a first order factor, it has an error of minus 3 dB at corner frequency. Suppose if it is a factor at numerator means here 0 dB up to corner frequency, actual plot is it will be 3 dB at corner frequency. Therefore, the error at corner frequency is 3 dB. Error at corner frequency is 3 dB. If you are not ignoring both omega tau as well as 1, you will get minus 3 dB instead of 0. Therefore, at corner frequency, you will get only minus 3 dB or plus 3 dB error. If it is denominator factor, minus 3 dB. If it is numerator factor, you will get 3 dB error. So, we can consider the approximate plot because of small error. Because of small error. Suppose if you want the actual plot means, you can do the necessary correction at corner frequencies. Necessary correction at corner frequencies. That's all. Let us consider a case g of s equal to k multiplied by tau 1 s plus 1 upon tau 2 s plus 1 multiplied by tau 3 s plus 1. For this, how to draw the Bode plot, let us see. Now, let us consider k equal to 1 and tau 1 equal to 10s plus 1. Here, we will get 5s plus 1. Here, we will get 20s plus 1. 20s plus 1. For k equal to 1 means 20 log k equal to 0. 20 log k equal to 0. That's why the plot for k is, when k equal to 1 means, the plot for k is at 0 dB, you will get a horizontal line. That's all. What is the plot for this 10s plus 1? What is the corner frequency for this? The corner frequency is 1 by 10. That is equal to 0.1. Let us say that this is 0.1, 0.01, 0.01. This is 0.1. This is 1. This is 10. This is 100. 1 by 5 is what? What is the corner frequency for this? 1 by 5. 1 by 5 equal to 0.2. What is the corner frequency for this? 1 by 20. 1 by 20 equal to how much? 0.05. 0.05. 0.05 is greater than 0.01. Am I correct or not? Okay. So everything is covered. So what is the plot for the numerator factor? What is the plot for the numerator factor? I am drawing the plot for numerator factor. Corner frequency is 0.1. Therefore, up to 0.1, it is 0. After that, it increases at the rate of 20 dB per decade. Am I correct or not? For this 5s plus 1, what is the corner frequency? 0.2. 0.2 is here. So 0.2 is here. Let us draw like this. To understand, let us put 0.1 here. This is 0.2. Corner frequency is 0.2 here. Corner frequency 2. This is corner frequency 1. This is corner frequency 3. Am I correct or not? I marked all these corner frequencies. Now I am going to draw the plot. The numerator, the corner frequency is 0.1. It is in the numerator. That's why up to 0.1, it is 0, approximate plot, asymptotic plot, Bode plot. Up to 0.1 is 0. After that, it increases at the rate of 20 dB per decade. It increases at the rate of 20 dB per decade. What is the plot for this? What is the plot for this? Corner frequency is 0.2. 0.2. Therefore, for that, it is up to 0.2, it is 0. After that, it decreases at the rate of minus 20 dB per decade. Up to 0.2, it is 0. After that, it decreases at the rate of 0.2, minus 20 dB per decade. The third case, 0.05 corner frequency. The third case is up to 0.05, 0. 0.050. After that, it decreases at the rate of minus 20 dB per decade. Am I correct or not? 3 plots I got. 4 plots actually. K equal to 1, that's why it is 0 dB always. 0 dB always. If you add all these 3 plots together, you will get the Bode plot for this. Bode plot for this you will get. You have to add all these together. This is for third factor. This is for second factor. This is for first factor. This is for first factor. This is for second factor. This is for second factor. This is for third factor. All the plots we have drawn separately, but we have to combine all these together. Here it goes up to infinity. It goes up to infinity. This goes up to infinity. This is also goes up to infinity. We have to add all these together. Up to 0.02, the second factor is 0. Up to 0.1, first factor is 0. Up to 0.05, third factor is 0. So after 0.05, some value is there. Am I correct or not? It is not 0. After 0.05, it is not 0. After 0.05, this factor is always there. I said it goes up to infinity. This factor is there. This factor is there. What is that? Third factor. The third factor corner frequency is 0.05. So after 0.05, this factor is always there. After 0.05, up to 0.05, it is 0. Therefore, we can draw like this. We can draw like this. So this is 0.05, corner frequency 3. This is the corner frequency 3. Up to this, it is 0. Up to this, it is 0. After that, it decreases at the rate of minus 20 dB per decade because it is in the denominator. It is 1 by 20s plus 1. 1 by 20s plus 1. For that, the corner frequency is 1 by 20 equal to 0.05. Up to corner frequency, it is 0. After that, it decreases 20 dB per decade. Here, up to what point? Up to 0.1. Up to 0.1. Here, this is 0.1. Up to 0.1, it decreases at the rate of, up to 0.1, it decreases at the rate of 20 dB per decade. After 0.1, you see that what happens after 0.1, it increases at the rate of 20 dB per decade. One is increasing, another one is decreasing. If you add these two together, it becomes 0. One is increasing, the speed is positive direction. Another one is speed is in the negative direction. Both are equal. If you add it together, what you will get? 0. Therefore, no increase or no decrease. Am I correct or not? No increase or no decrease. Therefore, after that it becomes horizontal. Why it becomes horizontal? For one factor, for this factor it decreases. For this factor, after 0.1 it increases. Both are at same speed. One is increasing at the rate of 20 dB per decade. Another one is decreasing at the rate of 20 dB per decade. If you add these two speeds together, what is the speed? 0. There is no change in speed. There is no change in speed. That's why it remains in the same speed at 0 dB per decade. The slope becomes 0 dB per decade. Up to what? Up to 0.2 only. Up to 0.2 only. At 0.2, what happens? All the three graphs come together. What is the slope of this? Minus 20 dB per decade. What is the slope of this? Plus 20 dB per decade. If you add these two together, 0 dB. The third one comes into picture, minus 20 dB. Therefore, after this, again, it decreases at the rate of minus 20 dB per decade. Here, it is 0 dB per decade. Here, it is minus 20 dB per decade. If you add all these together, we got this plot. So this is the plot for the given transfer function. Suppose k equal to 10. Suppose k equal to 10. 10, what is the first? 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. Now, earlier k equal to 1. That's why you got a horizontal line at 0 dB. Now, k equal to 10. For what is the k plot? 20 log 10. That is equal to 20 dB. Am I correct or not? For k plot, it is 20 dB per decade. 20 dB. That's all. 20 dB. This is the plot for k. Now I change the sum. The second sum is k not equal to 1. It is 10. All other factors same. All other factors same. For all other factors, you got this graph. You combined all the three, you got this. Now you have to combine k also. K is equal to what? K equal to 20 dB. Here you got a line. This is 0 dB. This is 0 dB. 0 dB. This is 20 dB. Now we have to add this k with this. It means what? The entire graph will lift up by 20 dB. The entire graph will lift up by 20 dB. That's all. So here, the 0 dB, it starts at 0 dB. Instead, it will start here. After that, it comes down like this. Then it will be a horizontal line. Then it will be. We shifted the entire graph by 20 dB. That's all. So, the k will shift the entire plot up or down. If k is greater than 1, it will shift the entire graph up. If k is less than 1, it will shift the entire graph by down. That's all. Now we got the Bode plot for 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. We got. This is the plot for k equal to 1. That is 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. That is the difference. If k is there, if k is greater than 1, the entire plot will shift up. Otherwise, it will shift down. That's all. This is to understand what is happening in the Bode plot. What is happening in the Bode plot? You can draw, if a transfer function is given without doing any calculation. If you know the corner frequencies, you can draw the Bode plot. For example, in this sum, let us assume k equal to 1. What are the corner frequencies? What are the corner frequencies? Corner frequencies are 0.1, 0.2, 0.05. Am I correct or not? This is for 1 by 10. This is for 1 by 5. This is for 1 by 20. This is for denominator. This is also for this is for numerator. This is also for denominator. Am I correct? 5 is for denominator. Am I correct? Yes. This is for denominator. This is for denominator. This is for numerator. So if I know the corner frequencies, first corner frequency is 0.05. So up to 0.05, it is 0. After that, up to 0.1, this is in the numerator, up to 0.1, it decreases at the rate of minus 20 dB per decade. It decreases up to what point? Up to 0.1. After that, up to 0.2, it is horizontal line, because both numerator, this is up to 0.1, it is in the numerator. At 0.1, it is in the numerator. Therefore, after that, it becomes horizontal. Again, up to 0.2, there are two terms in the denominator, one in the numerator. That's why 1 plus 20 and minus 20 getting cancelled. 1 minus 20 is there. Therefore, it decreases from 0.2. It decreases at the rate of minus 20 dB per decade. That's all. Now we will draw one K by 10s plus 1 multiplied by 0.1 s plus 1. What are the corner frequencies? Corner frequency is 1 by 10. First corner frequency is 1 by 10, that is 0.1. Second corner frequency 1 by 0.1, that is equal to 10. First corner frequency is 0.1. Second corner frequency is 10. So I can draw the Bode plot. Let us draw the Bode plot for this. What is the Bode plot for this? What is the Bode? K equal to 1. Let us assume that K equal to 1. 1 minute. K equal to 1. For that, what is the up to 0.1? It is 0. After that, it decreases at the rate of minus 20 dB per decade. This is carries up to 10. Up to 10. Here, the corner frequency is 0.1. Up to 10, it is decreases at the rate of minus 20 dB per decade. After that, it decreases minus 40 dB per decade. Why? Why? There are another denominator factor. Here, it decreases at the rate of minus 20 dB. After 10 radians per second, another factor comes. That's why it decreases at the rate of minus 40 dB per decade. Therefore, this is the plot. Without doing any calculation, we can draw the Bode plot. Actually, this way we have to draw the Bode plot. For examination point of view, we need some data for the examiner. That's why we will see some systematic method to draw this Bode plot in the next class. So far, we have seen how to draw Bode plot for 1 by s, first order factor in the denominator, first order factor in the numerator, repeated poles and the repeated zeros. In addition to that, we have seen first order system and first order factor in the denominator and numerator, that and all we have seen. Today, let us see how to draw Bode plot for second order system. Second order factor in the denominator as well as numerator. If you consider any transfer function, definitely there will be a gain. It may have poles at the origin. It may have poles at zeros at origin. Both may not exist, but anyhow, both may not exist simultaneously. One will get cancelled the other. Definitely n minus m poles will be there if m is less than n. And the first order factor in the numerator and the first order factor in the denominator and the repeated factors, that also we have seen. Now let us see second order factor in the denominator, that is tau 3 s square, tau square s square plus 2 zeta omega, sorry, 2 zeta tau s, 2 zeta tau s plus 1. This is second order factor in the denominator. Or T4 s square plus 2 zeta tau s plus 1. Why this happens while factorizing means if the poles are real, you will get the first order factor. The poles are complex, we won't convert into factor. In that case, we'll keep it as second order factor. That's why if you factorize a given transfer function, the possibilities are, these are the possibilities. For that, already we have seen 1 by s, s in the numerator, k, first order factor, repeated factors, that and all we have seen. Only pending is this. So g of s equal to 1 upon tau s square s square plus 2 zeta tau s plus 1. If this factor is there, what is the Bode plot that we are going to see today? If you convert this into sinusoidal transfer function, replace s by j omega, then what you will get? Minus omega square t square for this plus 2 zeta j 2 zeta tau omega plus 1. This you will get. What is modulus of g of j omega? Modulus of g of j omega equal to 1 upon square root of real part square, that is 1 minus omega square t square is the real part, whole square, plus imaginary part is 2 zeta tau, imaginary part is 2 zeta tau omega. So that square 4 zeta square tau square omega square, that is imaginary part. This is modulus of j of j. If you write this in decibel, 20 log 1 by, this is equal to 20 log 1 by square root of 1 minus omega square t square whole square plus 4 zeta square t square omega square. In dB, decibel scale. In that case, again, we will consider two cases. One is omega tau is far, far greater than 1. Omega tau is far, far greater than 1 means the zeta is always less than 1. Here, what you will get is omega power 4, 20 log. This 1 becomes negligible because as omega tau is far, far greater than 1. That's why 1 becomes negligible. This becomes omega power 4 square root of omega power 4 t power 4 plus 4 zeta square t square omega square. This is also negligible. We'll compare with omega power 4 t power 4. 4 zeta square t square omega square also negligible because fourth power is second power multiplied by zeta, that is less than 1. That's why this is also negligible. That's why this becomes that is approximately equal to 1 by 20 log 1 upon square root of omega power 4 t power 4 omega square t square. This is approximately equal to this. That is equal to 20 log omega square t square. If it bring to the numerator, you will get minus sign to the power minus 1. Therefore, minus 20 log omega square t square. If you bring this t square, if you write instead of omega square t square, if you write omega, this is also equal to minus 20 log omega tau whole square. Omega tau whole square. Therefore, this becomes minus 40 minus 40 minus 40 log omega tau. Now we will substitute omega equal to 1. Omega equal to 1 by t. If you substitute, what you will get? When omega equal to 1 by tau, if you substitute 1 by tau, this becomes 1. Therefore, you will get 20 log modulus of g of j omega equal to minus 40 multiplied by 0 equal to 0 dB. When omega equal to 10 by tau, if you substitute 10 by tau, you will get 20 log modulus of g of j omega equal to minus 40 multiplied by 1, that is equal to minus 40 dB. When omega equal to 100 by tau, another 10 times increase, you will get 20 log modulus of g of j omega equal to minus 40 log 100 means 10 square, that is equal to minus 80 dB. Log 10 equal to 1, that square becomes multiplication, that's why minus 80 dB. So the slope is, it increases at the rate of 40 dB per decade. Another case is when omega tau is far less than 1. This 1 is considered, this omega square t square, this both are negligible. That's why 1 you will get. Root 1 is 1. Therefore, 20 log g of j omega equal to minus 40 multiplied by 0 equal to 0 dB. Therefore, what is the plot for the second order? The plot is 0.1, omega equal to 0.1, 1, 10, 100 log omega, logarithmic scale. Here, let us assume that this is 1 by t, because we do not know the value of t. 100 by t, 0.1 by t. Up to 1 by t, it is 0. Up to 1 by t, it is 0. Up to 1 by t, it is 0. 0 dB. After that, it decreases at the rate of minus 40 dB per decade. Minus 40 dB per decade. If you find the error, what is this is the plot up to corner frequency 0. After that, it decreases minus 40 dB per decade. If you consider complete 20 log g of j modulus of g of j omega equal to 20 log minus 20 log square root of 1 minus omega square t square whole square plus 2 zeta 4 zeta square t square omega square. If you consider complete of this, it is function of zeta. It is function of zeta. Zeta value decreases, it is in the denominator. It is in the denominator. That's why as zeta value decreases, the magnitude will increase. The magnitude will increase. That's why the plot for zeta equal to 0.7 will be like this. The zeta for 0.7 will be like this. This is for zeta equal to 0.7. If you increase further, there will be a sluggish, maybe zeta greater than 0.7. If it decrease, what will happen? Suppose zeta is 0.2 means it will come like this. Zeta equal to 0.2. This is zeta equal to 0.5. Like that. So there will be a large error at corner frequency for second order system. That is the only drawback. Anyhow, for 0.7, it gives approximately this value. If zeta equal to 0.7, it gives almost minimum error. Suppose if you have a second order factor in the numerator, that is what g of j omega equal to g of j omega equal to g of j omega equal to tau square s square plus 2 zeta tau s plus 1. If you give like this, then what is the plot is just opposite to this. Here, it decreases at the rate of minus 40 dB per decade. Instead, it will increase. Therefore, the plot will be like this. Up to 1 by tau, it is 0 dB. After that, it increases at the rate of 40 dB per decade. This is second order factor in the numerator. Here also depends upon the zeta value. It will be like this. This is for 0.7. Zeta equal to 0.7. If zeta decreases, you will get like this. If zeta increases, you will get lag value. So error will be minimum when zeta is around 0.7. So approximate plot is this: up to 1 by tau, 0. After that, it increases at the rate of minus 40 dB per decade. That's all. We have seen all factors. Hereafter, we can draw Bode plot for any function. Before going that sum, the procedure to draw Bode plot, let us consider this g of s equal to k and tau s plus 1 and tau square s square plus 2 zeta tau s plus 1 upon s. Then tau 1, tau 2, tau 3 s plus 1. This is tau 4 s square plus 2 zeta tau 4 s plus 1. 4 time constants are there. Let us assume that T1 is T4 is greater than T2 greater than T3 greater than T1. Which is the smallest value? T1. T1 is the smallest value. Therefore, largest corner frequency is 1 by T1. Omega 4 equal to 1 by T4. Omega 2 equal to 1 by T2. Omega 3 equal to 1 by T3. Omega 1 equal to 1 by T1. If you write in terms of omega, omega 4 is the smallest. Omega 2 next. Then omega 3 next. Omega 1. Which is the largest? Omega 1 is the largest. So, what is the plot? Let us mark all the corner frequencies first. Omega 1 is largest. Therefore, first will be omega 4. Next will be omega 2. Omega 3. Then omega 1. Am I correct or not? Whether I correctly marked? Correctly marked. Except K, all other. One more is S is there. Except K and X, I marked all. for all factors. Omega 4 is what? For T4. Omega 4 is for T4. What is the corner frequency for this? What is the corner frequency for this? For this corner frequency is omega 4. Therefore, for this up to omega 4 it is 0. Am I correct or not? Up to omega 4 it is 0. After that it decreases. It will decreases at the rate of minus 40 dB per decade. Minus 40 dB per decade. It decreases at the rate of minus 40 dB. Minus 40 dB per decade because it is second order factor. That's why it decreases. But we can extend up to omega 2 only. Omega 2 is where? In the numerator. What is its slope? Plus 40 dB. That's why omega 2 to omega 3 again it will be horizontal line. Again it will be horizontal line. Omega 3 is again in the denominator but first order factor. That's why it will decrease at the rate of 20 dB per decade. Minus 20 dB per decade. It will go up to omega 1 only. At omega 1, again numerator factor. That's why 20 getting cancelled. Again it becomes horizontal. Again it becomes horizontal because for this 20 dB plus 20 dB per decade, for this minus 20 dB, for this minus 40, for this minus 40. So all equal, plus 40. This is plus 40. That's why all equal, that's why getting cancelled. Finally, it becomes horizontal. Suppose more denominator factor means finally it will decrease, further decrease. We plotted, if you know the corner frequencies, we can draw the Bode plot without doing any calculation. Now, how to incorporate K and the S? How to incorporate K and the S? What is K? For K is 20 log K in dB scale. In dB scale, 20 log K. 20 log K, K equal to 10 means it is 20 dB. 20 dB. This is the plot for K. This is what? 0 dB. Therefore, 20 dB will be here. 20 dB will be here. 20 dB. This is plot for K. This is plot for K. 20 dB. K equal to 10. That's why 20 dB. 1 by omega, 1 by S. For that, what is the plot? It is inclined at minus 20 dB per decade for the entire plot. Minus infinity to plus infinity, it decreases at the rate of, we have already seen. It decreases at omega equal to 1. At omega equal to 1, it crosses 0 dB. That is the only point that we know. When omega equal to 1, 1 by S means what? 1 by 1, 20 log 1 equal to 0. Therefore 0. It decreases at the rate of 20 minus 20 dB per decade. This is for 1 by S. I am writing a plot for 1 by S also. Let us assume that omega equal to 1 is here. Omega 4 is less than 1. Let us assume. Therefore, this is the plot for 1 by S. 1 by S. We have to add these three together. If we add these three together, we will get the complete plot. So I am telling you how to, if you know the transfer function, you can draw the frequency response. So for K, you have to lift everything by 20 dB. You have to lift everything by 20 dB. Therefore, 0 dB becomes 20 dB. Am I correct or not? If you lift the entire plot by 20 dB up, you will get 0 dB becomes 20 dB. That's all. So we included K. The only thing is we have to include that 1 by S. If you include 1 by S, what will happen? This horizontal line is, the slope is 0 dB per decade. But because of this, it becomes 20 dB per decade. Therefore, this becomes, this 0 dB becomes minus 20 dB per decade. This 40 dB becomes minus 60 dB per decade. This horizontal line again becomes minus 20 dB per decade. This minus 40 becomes, this 20 becomes minus 40. This horizontal line again becomes minus 20 dB per decade. The slope is now changed because of this 1 by S. The slope is changed. The slope is changed. So what we have to do is, now we have to shift this up by, so here we have to draw L. Here already this is shifted for 20 dB. Here instead of horizontal line, we have to draw yeah, 20 dB line. 20 dB line. Again, this becomes 60 up to omega 2. Again, this is 20 dB line. Again, this becomes 40 dB. This becomes 40 dB. Again, 20 dB. Like that, the slope will be changed 1 by S. The slope will be changed. So instead of horizontal line, its slope is minus 20 dB per year. Instead of 40 dB, it becomes 60 dB. So for the entire plot, we have to add 20 dB. So we can draw the rough plot. We can draw the rough plot. So how to draw that, we'll see here. 1 by K by S, we have to take. That K by S is, if you draw only for K by S, for K it is 20 dB, 1 by S at omega 1 equal to, you will get a 20 dB slope at, this is for 1 by S, its slope is minus 20 dB per decade. This is 0.1. That's why for K you will get a line here. For K equal to 10. That is 20 dB. If you combine these two, what will happen? If you add 20 dB at every point means this will shift up to by this, like this. This is 10 by S. Am I correct or not? This is 10 by S. Now we have to add the previous. This is omega 4. Omega 4. This is omega 2. Am I correct? Omega 2. This is omega 3 and this is omega 1. Now we have to add that previous plot. This has to be added. This is 40 dB up to omega 2 and then horizontal, then 20 dB, then horizontal. Now we have to add this and this. One more time we are seeing, that's all. So here, this is horizontal, this is inclined line. That's why this we have to take, that's all. This we have to take up to omega 4. After omega 4, what is the total slope? This is 20 dB, this is 40 dB, minus 40 dB per decade, because second order factor. This is 20 dB. Now we have to draw up to omega 2, 60 dB per decade. So up to omega minus 60 dB per decade. After this, what will happen? This is 0, but this is 20 dB. That's why from omega 2, we have to draw only 20 dB, minus 20 dB per decade. Up to omega 3. At omega 3, this is 20. This is also 20. Therefore, we have to draw at 40 dB. We have to draw at minus 40 dB per decade line up to omega 1. After omega 1, only 20 dB. Only minus 20 dB per decade. So, if you know K by S separately and all other factors separately, just we can add like this. So, this is, you should learn how to draw rough frequency response for given transfer function. But for examination, there is a procedure because they may expect if you draw directly, how the mark will be given. That's why we have to draw a table and how we are adding that and all we have to tell. That we will see now. First step 1, to draw Bode plot, step 1 is convert the given transfer function into time constant form. Because already I told you that in time constant form only K will be correct. K will be Correct. Therefore, the first step is we have to write in the time constant form. For example, G of S equal to 1 by S plus 5 is given. How to write this in time constant form? We have to take that 5 outside. So what you will get 1 by 5 S plus 1. 1 by 5 S plus 1. 1 by 5 S plus 1. Therefore, the transfer function becomes 1 by 5 divided by 1 by 5 S plus 1. This is time constant form. Therefore, earlier in this form, what is the gain? 1. It is not correct. The actual gain is 1 by 5, 0.2. Therefore, we have to write, the first step is we have to write in time constant form. Step 2. Step 2 is convert into frequency transfer function. Convert the given transfer function into frequency transfer function. That is S equal to J omega, you have to substitute. Substitute S equal to J omega. Then the next step is step 3. Find the time constant form in factorized form. Definitely they will give in factorized form. They won't give 10 S power 5, S power 6, they won't give because you cannot factorize. That's why they will give automatically factorized form. It is not factorized, you have to factorize. But it's very difficult to find the roots. That's why they won't give like that. If it is given, you have to find. But in factorized form, then the third step is find the corner frequencies. Corner frequencies. After finding corner frequencies, we have to draw a table. We have to form a table. The first column is given factor. Second one is corner frequency. Third one is slope contributed by the factor. This factor. I will explain what is that. Slope, then slope contributed by the given factor. This factor. In this case, the factor is 1 by 5 S plus 1. That is the given factor. Then net slope means as the corner frequency increases, what happens? The previous slope is added to the next slope. That's what we have seen. That the diagram is not there. So initially it is minus 40 dB. After that it becomes 0 because we are adding minus 40 and plus 40. Then again it becomes minus 20. Again it becomes 0 slope. So that is called net slope. Then frequency range are coordinates. The coordinates. That's all. The factor is, the first factor is K by S. No corner frequency for 1 by S. Therefore, we have to put a dash. The slope contributed by the factor is minus 20 dB per decade. Am I correct or not? Or you can put the unit here, dB per decade, and you can put simply minus 20. Net slope minus 20 dB. Before that, no factors. That's why. Now we have to find the coordinates. Second one is, suppose I am having a denominator factor 1 by 0.2 S plus 1. 0.2 S plus 1. Then what we have to do? Corner frequency is 0.5. Am I correct or not? Corner frequency is 1 by 0.2, that is 5. Slope contribution is minus 20 dB. Net slope is minus 40. Then third factor, suppose it is in the numerator, 0.02 S plus 1 in the numerator. What is the Corner frequency? 1 by 0.02. How much? 50. Therefore, the corner frequency is 50. The slope contributed is minus 40. It becomes minus 60. Huh? Oh, plus 20. Very good. Plus 20. That's why plus minus 20 again. Again minus 20. Suppose I am having a next factor is around 100. 100 means 1 by 100 equal to 0.01 S plus 1 in the denominator. So the corner frequency is 100. Slope is minus 20. Slope contributed by this is minus 20. What is the net slope? Minus 40. That's all. Now we have to find the coordinates. That's all. If you find the coordinates, you can immediately draw the root locus. What is the smallest corner frequency? 5. Smallest corner frequency is 5. That's why we can take a scale. From 0.1. I told you that no corner frequency is less than 0.1 means take from 0.1. Scale, x-axis scale must be taken from omega equal to 0.1. This is 1. This is 10. This is 100. This is 1000. Log omega scale. Now we have to find the coordinate at omega equal to 0.1 for the first case. Because we started where? 0.1. What is that factor? K by S. What is G of S equal to K by S? Am I correct? Let us assume that K equal to 20. Let us assume that 20 by S. Because everything we took number, that's why let us take 20 by S. Therefore, 20 by S. What is G of J omega? G of J omega equal to 20 by modulus of G of J omega, 20 by omega. 20 by omega. What is 20 log? 20 log modulus of G of J omega equal to minus 20 log plus equal to 20 log 20 by omega. Omega equal to 0.1, substitute and find the value. Substitute 0.1 for omega and find the value. 20 log 20 by omega. Minus 46.0. Definitely positive because 20 by 0.1 greater than 1 plus only. Minus 46. 26, 20. Okay, 46 is correct. Minus 46. Y coordinate is 46. What is the x coordinate? What is the x coordinate? 0.1, comma 46. I got the coordinate. Now let us find the second coordinate. Coordinate at this row. Let us find coordinate for this row. First row we find the coordinate. 0.1, comma 46. Next coordinate, we know the equation for, what is the equation for straight line? y2 minus y1 equal to slope multiplied by x2 minus x1. This is equation for straight line. These are all straight lines. That's why we can write the equation like this. Therefore, y2 minus y1 equal to slope multiplied by, this is in logarithmic scale. That's why log x2 minus log not x2, log omega 2, log omega 1. Therefore, you will get y2 equal to slope multiplied by log omega 2 by omega 1, because log omega 2 minus log omega 1 equal to log omega 2 by omega 1 plus y1 plus y1. Am I correct or not? This is the equation. By using this equation, we can find the coordinates. Where we have to find the coordinates? At corner frequency 5, we have to find. Therefore, we know the x coordinate. We know the x coordinate. Only thing is we have to find y coordinate. What is the formula? y2 equal to slope. What is the slope for this? Because after corner frequency 5 only, it becomes 40. After corner frequency only, it becomes 40. Before corner frequency, up to corner frequency, it is 0 slope. That's why whatever the previous factor slope only, it will contribute. That's why minus 20. Therefore, y2 equal to, we have to find. y1 equal to what? 46. Am I correct or not? y1 equal to 46. Omega 2 equal to 5. Sorry, omega at 5 we have to find. Omega 2 equal to 5. Omega 1 equal to 0.1. Am I correct or not? y1 equal to 46, because this is omega 1, this is y1. Now we have to, this is omega 2, y2 we have to find. y2 we have to find. Therefore, y2 we have to, in question, y1 is 46, omega 1 is 0.1, omega 2 is 5. Therefore, just to substitute this, y2 equal to slope. That is, only thing is you have to use this slope. This slope, previous slope we have to use, because up to 5 only we are finding. Therefore, minus 20, the formula is slope multiplied by log omega 2 is 5 divided by 0.1 plus 46. Find 12.0. Because log 50 is 1.6, you said. Multiplied by 10, 16. Multiplied by 2, 32. 46 minus 32, how much? 14. Rough calculation 14. So 12 will be correct. So y2 equal to 12. Therefore, the coordinate is the 5, 12. That's all. Now we have to find. Now we have to find the next coordinate. Next coordinate we have to find. Then what is this is omega 1. This is y1. Omega 2 equal to what? Omega 2 is 50. Omega 2 is 50. This is omega 2. This is y2. That's all. Find y2. y2 equal to, let us call this y2. The latest value is y2. You should remember like that. y2 equal to, what is the slope? Previous slope? To calculate this, we have to use this slope. Previous slope always you have to use, because up to 50 only we are finding. Up to 50 only. After 50 only, this factor will contribute. Why I am telling like that? This factor will contribute after corner frequency only. That's why that value we should not take. Previous value we have to take. So minus 40 log, that is omega 1 is 5, omega 2 is 50. Therefore, 50 divided by 5 plus y1 is 12. Find that. Minus 28. Log 10 is 1. 50 by 5 is 10. Therefore, minus 40 plus 12. Minus 28. Minus 28 dB. Therefore, the coordinate is 50, minus 28. Now we have to find the coordinate for the final. Again, we have to consider this as omega 1. This is y1. Omega 2 is what? Omega 2 is 100, y2 we have to find. Therefore, we can write y2 equal to y2 equal to, what is the slope? Previous slope we have to find. What is the previous slope? Minus 20, minus 20, minus 20 log 100 divided by 50, because omega 1 is 50, omega 2 is 100, plus y2 is minus 28. What is the value? Minus 34. Minus 34. One more coordinate we have to find, because we found up to 100 only. One more coordinate we have to find. After that, what is the slope? 40 dB per decade. Therefore, we can write after 100, what is the next decade? 1000, comma, add 40, minus 74. That's all. Minus 74. Because after that, it decreases at the rate of minus 40 dB per decade. Therefore, we can write like that. Now we have to draw the Bode plot. What are the coordinates? 0.1, 46, 5, 12, 50, 28, 100, 34, 1000, 74. That's all. We have to draw the Bode plot. What is the first coordinate? 0.1, 46. 46 dB. Then at 5, 12, at 5, 12, maybe 5 here. It is 12. At 5, this is 5, 12. Next one is minus 28 at 50. 50 means here. Minus 28. Maybe around here. Minus 28. Minus 28 at 50. Then minus 3400. At 100, minus 34. Maybe here. Minus 34. At 1000, it is 74. So it is here at 1000 minus 74. Minus 74. So we have to join all these lines. So this is the magnitude plot, Bode magnitude plot. That's all. So it is very simple. No need to understand anything. We have to fill this table. That's all. The first factor is if K alone is there, we have to write K alone here. K alone you have to write. If S or S square is there, we have to substitute. That's all. This first factor is K by S power N or K S power M. Suppose numerator factor alone is there. So all S factors, any pole or zero at origin must be combined with that, the first. All other factors, you have to write like that and fill the table and draw the Bode plot. Magnitude plot is over. What is the phase plot for this? What is the transfer function? The transfer function G of S equal to K, these two, 0.2 S plus 1. This is 0.01 S plus 1. This is 0.02 S plus 1. This is the given sum multiplied by S. Am I correct? So we have to write to find the phase plot G of j omega equal to K 0.02 j omega plus 1 whole divided by j omega 0.2 j omega plus 1 0.01 j omega plus 1. What is the angle of G of j omega? Angle of G of j omega equal to K 0 always. Angle for K is 0. That's why we can leave. For remaining thing, this is in numerator. That's why tan inverse positive plus tan inverse of 0.02 omega minus tan inverse of 0.2 omega minus tan inverse of 0.01 omega minus 90 degree. For this j omega, only imaginary part, that's why minus 9. That's all. substitute omega equal to 0.1. Here, substitute omega equal to 0.1, find the angle. Then substitute omega equal to 1. Always you have to find it for omega equal to 1. So substitute omega equal to 1 and find the angle. Substitute omega equal to 5, find the angle. Substitute omega equal to 50, find the angle. Substitute omega equal to 100, find the angle. Substitute omega equal to 1000, find the angle. And draw the phase plot. The phase plot will be like this. If you draw, it will be like this. So the final angle will be these two getting answered minus 180. The maximum angle will be minus 180 degree. The minimum angle is so you'll get substitute get some 4 or 5 values between 0.1 and 1000. 0.1, what is the angle? When omega, you form a table like this. A table like this. This is omega, angle of G of J omega. 0.1 we have to find. Then we have to find for 5. Then you have to find for 50, 100, 1000. And omega equal to 1 also you have to find. So I forgot. So omega equal to 1. Omega equal to 0.1. This is omega equal to 0.1. 0.1, 1, 5, 50, 100, 1000. You substitute, find the angles. For 1.1 you got. For 1 you got. For 5 you got. For 50 you got. And 100 also you got. 1000 also you got. So you can draw the phase plot. Minus 155 degrees. Both in the same y-axis will be same. You have to mark 155 here. Don't draw separately because these two must be with the same x-axis. You have to draw with the same x-axis. Y-axis only you have to give different scale. That's all. Minus 176 is the maximum value. Now only one simple point I will explain in the next class. But anyhow, how to find the gain margin, phase margin. Here, the phase margin is where it crosses 0 dB. Here it crosses 0 dB. Draw a horizontal vertical line and find the angle. Draw a vertical line and find the angle here. It may be minus, this angle may be minus 165, let us assume. I am not drawing to the scale, but above 155. Because for phi itself, minus 155. That's why above 155, I know. That's why I put minus 165. Therefore, the phase margin equal to 180 minus 165. That is equal to how much? 15 plus 15 degree. Phase margin is 15 degree. If you insert a phase shift in the feedback path, a 15 degree phase shift in the feedback path, the system becomes in the verge of instability. The system becomes in the verge of instability. Like that, we can find the gain margin. For this sum, the gain margin is infinity. I will explain why later. But gain margin, how to find gain margin, phase margin, we'll see in the next class. Morning we have seen how to draw Bode plot. Now let us draw Bode plot for given sum. Draw the Bode plot of the open loop transfer function. G of S equal to 200 multiplied by S plus 10 upon S multiplied by S plus 5 multiplied by S plus 20. The first step is we have to convert the given transfer function into time constant form. It is not in time constant form. This is not in time constant form. It is not in time constant form. That's why we have to convert this into time constant form first. So to convert this into time constant form, G of S equal to we have to take 5 and 20 outside, that is 100. S multiplied by 1 by 5 S plus 1, 1 by 20 S plus 1. Numerator 200 multiplied by 10, 1 by 10 S plus 1. So now it is in time constant form. What is the gain? Gain is 20. 20 multiplied by S by 10 plus 1 upon S multiplied by S by 5 plus 1, S by 20 plus 1. 3 first order factors are there, 2 in the denominator and 1 in the numerator. First, we have to prepare, we have to find frequency transfer function. 20 j omega plus 1 upon S multiplied by 0.2 j omega plus 1, 1 by 20, 0.05. S plus 1. Therefore, the table now we have to prepare. Number of factors. Then, what is the factor we have to write? Corner frequency we have to write. Then net slope contributed by this factor in dB per decade. Net slope. Then coordinate. The first one is 20 upon j omega. First factor is 20 upon j omega. No corner frequency. No corner frequency. The slope is, it is in the denominator, that's why minus 20 dB per decade. Net slope also minus 20 dB per decade. Coordinator, we have to find the corner frequencies are, 5, 10 and 20. 5, 10 and 20 are the corner frequencies. Lowest is 5. Therefore, we have to start with 0.1. 0.1 comma y coordinate we do not know. We'll find later. Then second factor is lowest corner frequency we have to write first. Lowest corner frequency that we have to write first. What is the lowest? 5. 5 means we have to write 1 by j omega plus 5. Or you can write 0.2 j omega plus 1. So let us write in time constant form. So the corner frequency is 5 minus 20, therefore minus 40, and the coordinate is 5 comma. The next one is 0.1 j omega plus 1 plus 0.1 j omega plus 1. Corner frequency is 10 plus 20. That's why minus 20, 10 comma. The fourth factor is 1 upon 0.05 j 0.05 omega plus 1. The corner frequency is 20. Then net slope, the slope contributed is minus 20. Therefore, net slope is minus 40. And the coordinates 10, comma, and 100, comma. Final, that's why 2 coordinates we have to find. That's all. Now we have to find the coordinates one by one. Here, if you find the dB scale, this 20 by omega, that is 20 log 20 by omega, that is equal to omega equal to 0.1, because the scale starts with 0.1, because lowest frequency is 5 only. That's why we will start with 20 log 0.1, sorry, 20 divided by 0.1 equal to how much? (46 dB). 46 dB. Therefore, the coordinate is 0.1, comma 46. The next here we have to find for that, this is omega 1, omega 2, y1, y2 we have to find. Y2 equal to, what is the slope? We have to consider the previous slope, that is minus 20 log of omega 2 by omega 1, 5 divided by 0.1 plus y1, that is 46, equal to how much? 12 dB. So here you will get 12. Again, y2 equal to, this is omega 1, this is y1. We have to find y2, that is minus, that is previous slope is minus 40 log omega 2 is 10 by 5 plus y1 is 12, that is equal to minus 0.04. Here 0.04, but minus. Y2 equal to, the previous slope we have to put minus 20 log omega 2 is 20 divided by 10 plus minus 0.04, that is equal to how much? Minus 6. Minus 6. Now for 200, it is simple. For 200, what is the slope? Minus 40. After that corner frequency, it is minus 40. We have to add, here it is minus 6, minus 6, minus 40, minus 46. That's all. Now we have to draw the magnitude plot. We have to draw the magnitude plot. 0.1, 1, 10, 100 log omega. What are the coordinates? 0.1, 46, 46 dB scale. Then 0.1, 46, 5, 12. 5 will be around here. For 5, 12. Then 10 minus 0.04. 10 minus 0.04. Minus 0.04. Then 20 minus 6. 20 is around here. minus 6 and 40, 100, 200 will be here. 200 is about minus 46. So we have to join all the lines to get the plot. This is magnitude plot. Now we have to draw the phase plot. To draw phase plot, we have to consider this. So angle of G of j omega equal to, there is no angle for 20. Angle for 20 is 0 because only real part. Here 0.1 omega by 1. Tan inverse of positive. Tan inverse of 0.1 omega minus tan inverse of 0.2 omega. 0.2 omega minus 0.05 omega. Tan inverse of 0.05 omega minus 90 degree. Because for this j omega, you will get 90 degree. So here, now we have to prepare the table for phase omega, angle of G of j omega. Both we have to write. We have to find for 0.1. We have to find 1, 5, then 10. We have to find where it crosses. Generally, we have to see where it crosses. It actually crosses at this is 0.1, 1, 10. Actually, it is crossing at 10. If you know where it crosses 0 dB, that point also you have to include. That point also you have to include. I will let you know later why. 0 crossing. That frequency also you have to include. That frequency is called omega GC. That frequency is called omega GC. Here it is 10. That's why I'm not including that omega GC. Then you have to include 10. Then what is there? 20 is there. Then 200 is there. That's all. For all this, you have to find the angle. For all this, you have to find the angle. If you put infinity, what you will get? You can include infinity also. Final angle. If you put omega equal to infinity, this becomes 90. This becomes 90. This also becomes 90. These two are negative. Minus 90, plus 90. So 3 minus 90, 1 plus 90, therefore 180. As omega tends to infinity, the final angle of G of j omega equal to minus 180 degree. So that also you can include minus 180 degree. If omega equal to 0, what you will get? Angle. Tan inverse of 0 is 0. When omega tends to 0, angle of G of j omega equal to minus 90 degree. That's why it will start at minus 90, end at minus 180. So all these values must be between minus 90 and minus 180. If you get any other value, maybe mistake. That's why you should be careful. So for that, it is better to find for omega equal to 0 and omega equal to infinity, so that you will know the range of angle. So the range of angle is minus 90 to minus 180. If you get any other angle, it's wrong. Find the angle. For all corner frequencies, we got the angle. Now we can plot the phase plot. This is the phase plot. This is the actual plot drawn on semi-log sheet. Now we have to find the gain margin and phase margin. Here, to find the gain margin and phase margin, to find the gain margin, where it crosses 180, we have to see. Where it crosses 180 at infinity only. Where it crosses, because its maximum value, maximum angle is 180. That's why it crosses at 180 only. Therefore, here at infinity, it crosses minus 180. Where it crosses 180, we have to check. At that point, what is the magnitude? This also went to infinity, because the magnitude also went to infinity. The magnitude also went to minus infinity. Therefore, gain margin is infinity. This you may not be able to understand now. We'll see later. I'll make you understand this gain margin infinity later. Phase margin. To find phase margin, where it crosses 0 dB, we have to check. 0 dB, here it crosses. There you have to draw a vertical line. There we have to see the angle. Angle is 1 division above 150, therefore minus 140. Minus 140. Therefore, phase margin equal to 180 minus 140, 40 degree. Therefore, phase margin is 40 degree and the gain margin is infinity. Gain margin infinity means you can increase K any amount of value. It will not become unstable. In other words, the root locus will not cross the j omega axis if you increase the gain. But there is a threat in the phase. If we introduce a phase shift in the feedback loop about 40 degree, minus 40 degree, then this minus 40 becomes, this minus 140 becomes 180, minus 180. If we introduce a phase shift, it becomes 180. That's why it becomes in the verge of instability. So in two ways, you can bring the system to instability. One is by increasing gain, that you can understand from gain margin. Another reason is by introducing phase shift. If you introduce a phase shift of 40 degree, additional phase shift of 40, already it has a phase shift of minus 140. If you introduce additional phase shift of 40 degree, it becomes in the verge of instability. Even though it doesn't become unstable for if you increase any amount of K. But if you increase phase shift, it becomes unstable. That is called gain margin and phase margin. Only I have to explain what is gain margin. That is the next slide. But the want of time today, we cannot see. Tomorrow we'll see what is gain margin and phase. Today we are going to discuss about gain margin, phase margin in Bode plot. Gain margin. Gain margin is the open loop gain, static gain that can be increased. The amount of static gain that can be increased so that the system will be in the verge of instability. That is called gain margin. In Bode plot, we can find the gain margin in decibel scale. To find the gain margin, we have to consider both magnitude plot as well as phase plot together. This is the Bode plots for phase and magnitude of a system whose open loop transfer function is 1 upon S multiplied by S plus 1 multiplied by S plus 2. This is the open loop transfer function. For that, this is the top one is the magnitude plot and bottom one is the phase plot. Both has the same common x-axis, y-axis having different scale.
For magnitude plot, it is in decibel. For phase plot, it is in degrees. But x-axis is common. This is not 1. This is 0.1. This is 1. This is 10. Here, the first step is to find the gain margin is the phase plot at 180 degree. Draw a horizontal line at 180 degree. That cuts the phase plot at A. Draw a vertical line at A that will meet the magnitude plot at B. At B, draw again another horizontal line to find the magnitude at B. The magnitude at B is minus 15.57. Therefore, the gain margin equal to minus of minus 15.57 equal to 15.57 dB. That is the gain margin. The meaning of this gain margin is if we increase the static gain in the closed loop, that is 15.57 dB, closed loop gain is increased, static gain is increased, then the system will be in the verge of instability. That is the meaning. It is in decibel scale. This is equivalent to finding the gain in root locus or Routh array. It is equivalent to finding gain in Routh array. That is Kmax. For Kmax, the system will be in the verge of instability and its poles will be on the j omega axis. The poles will be on the j omega axis. That Kmax we can found by Routh array. That is, the poles will be exactly on the j omega axis. This is third order system. That's why one pole is at origin, another pole at -1, and the third pole is at -2. Between -1 and 0, it is part of root locus because 2 is the right odd number of poles. Similarly, after -2, it is part of root locus up to -infinity. There is a breakaway point and it goes to right hand side. The poles will be exactly at the j omega axis at Kmax. This Kmax can be found by Routh array. What is the denominator polynomial of this system? The denominator polynomial of open loop system is s cube plus 3s square plus 2s. This is open loop transformation. Numerator k. As k varies from 0 to infinity, we got the root locus. Therefore, denominator polynomial, characteristic polynomial is s cube plus 3s square plus 2s plus k. That is written here. For that, if we form the Routh array, coefficient of s cube is 1, coefficient of s square is 3, coefficient of s is 2, then constant term is k. If you find this is s cube row, this is s square row, s power 1 row, if you find, what you will get 6 minus k divided by 3. 6 minus k divided by 3. S power 0 row, s power 0 row is, you multiply these two minus 0, 3 multiplied by 0 is 0, divided by k is, you will divided by 6 minus k divided by 3 is, you will get k again. So for a stable system, this first column of a Routh array must be positive. Therefore, the condition is k must be greater than 0. The second condition is 6 minus k by 3 should be greater than 0. That is 6. K should be less than 6.
K should be less than 6. Therefore, when K is between 0 and 6, the system will be stable. When K equal to 6, that is K max. K equal to K max equal to 6, the poles will be exactly on the J max axis. The system will be in the verge of instability that we know. The same can be found from gain margin. Gain margin, how much? That is 15.57. This much is the gain margin. If we increase the gain of the system by this much, then the system will be in the verge of instability. That is in logarithmic scale, that is decibel scale. This is in dB scale. To find the linear gain, 20 log K equal to 15.57. Therefore, K equal to 15.57 divided by 20. If we take anti-log on both sides, K equal to 10 power 15 by 20. 10 power 15.57 divided by 20. That is equal to 6. We got the same answer. In both methods, it means gain margin means the amount of gain that can be increased in a closed loop system so that the system will be in the verge of instability. That is, the poles will be exactly on the J max axis. The gain will be K max. That is the meaning of gain margin. This can be found this way. Similarly, if you increase any further above 15.57, the system will become unstable. The system will become unstable. In the same way, we can find phase margin. The same way we can find phase margin. To find phase margin, at 0 dB, we have to draw a horizontal line. To find phase margin, we have to start in magnitude plot. To find the gain margin, we have to start in phase plot. Just opposite. So draw a horizontal line at 0 dB. It meets the magnitude plot at C. At C, draw a vertical line. Draw a vertical line. It meets the phase plot at D. At D, a horizontal line. Draw a horizontal line. That gives the value phase at D. The phase at D is minus 126.55. Therefore, phase margin equal to 180 plus 5. That is 180 minus 126.5. That is equal to 53.5 degree. That is the phase margin. The meaning of phase margin is, suppose we are having a system like this. We are having a system like this. R of S, K. This is the open loop system, G of S. Now it is in closed loop. If you increase K, that is K max equal to 6, the system will be in the verge of instability. It will exhibit sustained oscillation. Or without increasing this gain, you are not increasing the gain, keeping the gain as such. That is in this case 1. But if you increase the phase shift, if you increase the phase shift of the system by 53.5, if you increase the phase shift to 53.5 degree, then also the system will be in the verge of instability. So without increasing the gain, if you introduce the phase shift in the system, additional phase shift of minus 53 point, that is very important, minus 53.53, 53.5 degrees in phase shift, then also the system will be in the verge of instability. That is the meaning. So, therefore, it requires additional phase shift to drive the system in the verge of instability. If you see the gain margin, it requires additional gain of 15.57 dB to drive the system in the verge of instability. Both gain margin and phase margin are positive. Gain margin is 15.57 positive value. Phase margin is 53.5 positive value. Both values are positive. Therefore, the given system is stable and has a gain margin of 15.57 and phase margin of 53.5. If any of these values are negative, the system is unstable. Already it crossed j omega axis. That is the meaning. The system is in the unstable region. If it is negative value, any one of these two are negative or both are negative, the system is unstable. The system is unstable. Here, to find gain margin at minus 180, we have drawn a horizontal line. It cuts A. It cuts the phase plot at A. The frequency at the phase plot A is called phase crossover frequency. So we have to find the gain margin at phase crossover frequency. At phase crossover frequency. Phase crossover, it crosses 180 degree. Phase crossover frequency. Similarly, at 0 dB, if you draw a horizontal line, it cuts the magnitude plot at C. At this frequency, we have to find the gain, that is minus 136.5. We found that C is called omega GC, gain crossover frequency. Gain crossover frequency. We have to find the phase margin at gain crossover frequency. So that's why the phase crossover frequency is to find the gain margin. Gain crossover frequency is to find the phase margin. Let us increase the gain. We know that the maximum gain is 6. The gain should be less than 6 for a stable system. Now let us increase this gain from 1 to 15 and we will draw the Bode plot and check the gain margin and phase margin. This is the plot for 15. The gain is increased to static gain is increased to 15. For that, we have drawn the Bode plot, magnitude plot, as well as phase plot. Phase plot. Draw a horizontal line at 180 degree. 180 degree. That cuts the phase plot at A. That is called phase crossover frequency. In this case, this is 1, this is 2, this is 1.5 radians per second. So, phase crossover frequency, omega PC is 1.5. Draw a vertical line. It cuts the magnitude plot at B, omega PC. At omega PC, draw a horizontal line. Draw a horizontal line that meets y-axis at 10. Therefore, gain margin equal to minus of plus 10. That is equal to minus 10. Negative value. Therefore, unstable system. Gain margin is negative. Because we increase the gain to 15. Maximum gain is 6. But we increase to 15. That's why this becomes unstable. Let us find the phase margin. At 0 dB, draw a horizontal line. At 0 dB, draw a horizontal line. It cuts a magnitude plot at C. Draw a vertical line at C. Draw a vertical line at C. It meets the phase plot at D. Draw a horizontal line again at D. This gives minus 200 degree. Minus 200 degree. So what is the phase margin? Phase margin equal to 180 plus 5. That is equal to 180 minus 200. That is equal to minus 20 degree. That is again negative. Therefore, the system is unstable. We know that if we increase beyond 6 dB, this will be unstable. We got the same. So the point D is called gain crossover frequency. Gain crossover, gain omega GC. if omega GC is greater than omega PC, unstable, we can easily say. Omega GC is greater than omega PC, then also we can say that unstable. Here you see that omega GC is less than omega PC. Here omega GC is greater than. That's why we can say that way also we can say the system is unstable. If negative value says unstable. That's all about gain margin and phase margin. Another way of understanding phase margin is we know that the Nyquist plot, polar plot for the given system. This is the polar plot for 1 by s multiplied by s plus 1 multiplied by s plus 2. Order is 3, type number is 1. Order is 3, type number is 1. 0 degree, 180 degree, 270 degree, 360 degree. Or you can say that minus 90, minus 180, minus 270. Like that we can say. So here modulus of g of j omega equal to 1 upon omega square root of omega square plus 1 square root of omega square plus 2. If omega equal to 0, it becomes infinity. Angle of g of j omega. This is the polar plot. Polar plot, or can call it as Nyquist plot. It is part of Nyquist plot. That's why it can also be called as Nyquist plot. When omega equal to 0, angle equal to minus 90 minus tan inverse of omega minus tan inverse of omega by 2. If omega equal to 0, you will get minus 90 degree. So magnitude is infinity, angle is minus 90. That's why it is coming from 90 degree at infinity. When omega equal to infinity, what you will get? The modulus of g of j omega. When omega tends to infinity, what you will get? If you substitute infinity, it becomes 0. Angle of g of j omega, what you will get? Angle of g of j omega equal to omega tends to infinity. You will get this is also minus 90, this is also minus 70. Therefore, minus 270 degree. Minus 270 degree. Minus 270 degree. So, we got this plot. For intermediate values lies in between minus 90 and minus 270. Magnitude also from infinity to 0. You got this plot. This is plotted on a polar chart. This is the unit circle. This is the unit circle. This is the unit circle. Minus 1 plus 1 plus j minus j. This is 1. That's why stable system. That's why it doesn't encircle. It doesn't encircle the minus 1. Therefore, stable system. Stable system. If you increase gain, it will amplify like this. It will amplify. If you increase the gain to 6, it will pass through this way. If you increase gain to 6k equal to 6, if you increase k equal to 6, it will pass through minus 1 and it becomes in the verge of instability. In the same way, we can say that if you increase the phase shift, now the phase shift is at this point minus 126.5. If you increase the phase shift to another 53.5, minus 53.5, this point this point will move along this unit circle to -1. That's why if we, without increasing gain, if we increase the phase shift to 53.5, the system will be in the verge of instability. If the plot passing through -1 means it is in the verge of instability. If it is passing before -1 means stable. If it is passing after -1 means unstable. So if we increase the phase shift by -53.5, this point will move along this unit circle and it will reach -1 without increasing gain. That is to understand what is phase margin. So if we can explain phase margin by using polar plot or Nyquist plot easily. Nyquist plot easily. That's why I explained this with the help of Nyquist plot. Good afternoon. We are going to see sums on Bode plot. Sketch the plot is showing the magnitude in decibels, phase angle in degrees as a function of frequency in logarithmic scale for the transfer function given by g of s equal to 10 upon s multiplied by 1 plus 0.5 s multiplied by 1 plus 0.1 s, and hence determine the gain margin and phase margin of the system. Here, nowhere it is mentioned that Bode plot. So we should know the meaning of Bode plot. Bode plot means x-axis is in logarithmic scale, y-axis in decibel means it is Bode plot. So he is indirectly saying Bode plot. That's why a note is given in that sum, draw Bode plot. The first step is to draw the Bode plot. The very first step is it should be in time constant form. Is it in time constant form? Yes. Yes, it is in time constant form. That's why no problem. You can take as such g of s equal to 10 upon s multiplied by 0.5 s plus 1, 0.1 s plus 1. Then step 2 is we have to write frequency transfer function 10 upon j omega j 0.5 omega plus 1 j 0.1 omega plus 1 frequency transfer function. Then the step 3 is we have to find the corner frequencies. Corner frequencies are corner frequency 1 is 1 by 0.5. 1 by 0.5, that is equal to 2, and corner frequency 2 equal to 1 by 0.1 equal to 10. So 2 and 10 are corner frequencies. So now we have to form the table. Factor, then slope contributed by the factor in dB per decade, net slope, then we have to find the coordinates. We have to write the factors. Oh, one more column. It is corner frequency. Corner frequency. Always the first factor is K 10 by S. 10 by S. The next factor is the corner frequency must be in ascending order. So first we have to write for 2. Therefore, 1 by 0.5 s plus 1. That is Corner frequency is 2. The next factor is 1 by 0.1 s plus 1. Here the corner frequency is 10. So the corner frequency, no corner frequency, 2, 10. The corner frequency must be in ascending order. Ascending order. So what is the slope contributed by 10 by s? Minus 20 dB per decade. Net slope also minus 20 dB. Again, 0.5 s plus 1. What is the slope contributed by? Minus 20. Therefore, net slope is 40. The slope contributed by this 1 by 0.1 plus s is again minus 20. The total is 60, minus 60. Now we have to find the coordinates. We have to find the coordinates. Coordinates are, what is the lowest corner frequency? Lowest corner frequency is 2. Therefore, we have to start with the 0.1. Therefore, the coordinates here are 0.1, comma. Here the coordinates are 2, comma. Here coordinates are 10, comma, and 100, comma. 10 and 100, comma. That's all. Now we have to find the coordinates. Here, to find the coordinate, 10 by j omega. This also can be written as 10 by j omega. So in both ways we can write. Therefore, here the coordinate y2 equal to 20 log modulus of g of j omega, that is equal to 20 log k, that is 10 by omega. That is equal to what? That is equal to 20 log, coordinate is 0.1. 10 by 0.1. 10 divided by 0.1. That is equal to 20 log 100. That is, if 20 log 100 means, what you will get? 40 log 40 dB. So it starts with 40 dB. Starts with 40 dB. Therefore, omega 1, y1, omega 2, y2 we have to find. This coordinate we have to find. Y2 equal to, we have to use the previous slope. Therefore, minus 20 multiplied by log omega 2, 2 by 0.1 plus y1 is 40. That is equal to 14. Therefore, the coordinates are 2, 14. Then we have to find for 10. Therefore, omega y2 equal to slope. What is the previous slope for this? This is the previous slope. This is the previous slope. Therefore, minus 40 log omega 2, that is 10 divided by 2 plus y1 is 14. That is equal to minus 14. That is equal to minus 14. Therefore, the coordinate is minus 14. Minus 14. Now we have to find for 100. 100, what is the slope? 60 dB per decade. After 1 decade, minus 60 minus 14, minus 74. So we got that. Now we can draw the magnitude plot. What is the magnitude plot? We have to take axis from 0.1, 1, 10, 100, 1000, like that. So here
up to what is the first coordinate? First coordinate is 0.1 comma 40. At 0.1 it is 40 dB. That is log omega. Next coordinate is 2 comma 14. 2 here 2 comma 14. Then this is 14. Then next coordinate is 10 minus 14. 10 minus 14. 10 minus 14. Then 100 minus 74. Therefore, the plot is like this. So this is the magnitude plot. Now we have to draw the phase plot. Phase plot, what is G of j omega? G of j omega equal to what is the transfer function? 10 upon j omega 0.5 j omega plus 1, then 0.1 j omega plus 1. So what is the angle of G of j omega? Therefore, angle of G of j omega equal to, for this angle is 0, for this angle is minus 90 degree, minus, why minus? Because denominator, tan inverse of 0.5 omega minus tan inverse of 0.1 omega. That's all. Now we have to form a table for phase plot. Omega, angle of G of j omega. That is equal to, first let us find for 0.1. 0.1, the angle is, if you substitute here omega equal to 0.1, you will get minus 93. Then if you substitute 0, what you will get? Omega equal to 0, you will get minus 90. As omega tends to 0, angle G of j omega equal to minus 90. So it should be above minus 90 only. So 0.1 minus 93. Then 0.1 equal to minus 1 minus 122 degree. Then 10 minus 214 minus 214 degree. 100 minus 264 minus 264. And infinity, if you substitute infinity, this also, this tends to infinity, you will get minus 90. If this tends to infinity, you will get minus 90. So minus 270 you will get. So it varies from minus 90 to minus 270. So now we have to draw the phase plot. Phase plot. For phase plot, it varies from minus 90 to minus 270. It will be looking like this. The actual plot is like this. Now we have to find the, what is the question? Find the gain margin and phase margin. Find the gain margin and phase margin of the system. How to find how to find gain margin and phase margin? To find gain margin, we have to draw a horizontal line at 180 degree. It meets at A. At A, draw a vertical line. At A, draw a vertical line. Draw a vertical line. It
meets here at B. Draw a horizontal line at B that gives the value minus 1.5 dB. Therefore, gain margin equal to minus of minus 1.5, that is equal to 1.5. Gain margin. How to find phase margin? At 0 dB, draw a line that will meet the magnitude plot at C. Draw a vertical line that will meet the phase plot at D. At D, what is the angle? You have to see that angle is minus 176. Therefore, phase margin equal to 180 minus 176. That is equal to 4 degree. Both are positive. Both are positive. Therefore, stable system. Stable system. One more thing we have to note here, the horizontal line, 180 degree horizontal line cuts the phase plot at A. That A is called omega PC, phase crossover frequency. The point C, 0 dB line cuts the magnitude plot at C. The point C is called omega GC, gain crossover frequency. Gain crossover frequency. So gain margin equal to plus 1.5, phase margin equal to 4 degree. The open loop transfer function of a unity feedback system is G of S equal to 5 divided by S multiplied by S plus 1, S square plus 2S plus 5. This is given. This is given. Using Bode plot, this exact plot we will see later. By using Bode plot, find gain margin, phase crossover frequency, gain crossover frequency. All these we have to find. How should the gain be adjusted so that the gain margin becomes 10 dB? We have to adjust K so that the new gain margin becomes 10. Another, how should the gain be adjusted? We have to adjust K so that the gain crossover frequency is 1.2 radians per second. Gain be adjusted, how the gain should be adjusted in the system so that phase margin is 45 degree. How to adjust K? So we have to find the 3 Ks. One is for the given gain margin of 10. Another one is for given gain crossover frequency of 1.2 radians per second. Another one, we have to adjust the gain so that phase margin is 45 degree. That and all we will see after drawing that Bode plot. To draw that Bode plot, the first step is convert the given. Step one is convert the given transfer function into time constant form. Time constant form. Therefore, here this is in omega n square, s square plus 2s plus 5 is given. So it should be 1. Therefore, we can write 1 by 0.2 s square plus here 2 by 5 0.4 s plus 1. We are taking that 5 outside. So if you write the given transfer function in time constant form, what we will get is 5 divided by 5 multiplied by s plus 1, 0.2 s square plus 0.4 s plus 1. Here 5 getting cancelled. Now it is in time constant form. So what is G of j omega? Step 2. Step 2 is G of j omega equal to 1 upon frequency transfer function. J omega plus 1 minus 0.2 omega square plus 0.4 j omega plus 1. This is the frequency transfer function. Here, omega 1 equal to 1 by 1 equal to 1. Omega 2 equal to 1 by, this is t square, square root of 0.2. 1 by root 2 equal to 2.3. Second corner frequency is 2.3. So now we have to form the table. Table is serial number. First factor 1 by j omega. Factor. Second factor is 1 by j omega plus 1. And the third one is 1 by minus 0.2 omega square plus 0.4 j omega plus 1. So corner frequencies are no corner frequency for this factor. Here corner frequency is 1. Here the corner frequency is 2.3. 2.3. Now slope contributed by each factor. Here minus 20, minus 20, minus 40 because second order. So net slope contributed by each factor is minus 20, minus 40, minus 80. Now we have to write the coordinates. If you know the coordinates, we can draw the Bode plot. The coordinates are, what is the lowest corner frequency? 1. Therefore, we have to start with 0.1. 0.1. Here 1. Here 2.3. Then 23. 2.3 and 23. and 23. So these are the coordinates that we have to find. The first coordinate is what? This coordinate y equal to 1 by 20 log 1 by omega. That is equal to 20 log 1 by 0.1. That is equal to 20 log 10. That is equal to 20 dB. Therefore, the coordinate here is 20. The coordinate here is 20. The next one is, now this becomes omega 1. This is omega 1, y1, omega 2, y2. Therefore, y2 equal to 20, sorry, what is that? Here we have to use this slope, minus 20 log omega 2, that is 1 by 0.1 plus 20. That is equal to, this is 1 by 0.1 is 10, log 10 equal to 1. Therefore, minus 20 plus 20 equal to 0. Therefore, the coordinate here is 0. The next coordinate. Then this becomes This becomes omega 1 and this becomes omega 2. This becomes omega 1 and this becomes y1. This is y1. This is omega 2 and y2. Therefore, y2 equal to, what is the previous slope? We have to use the previous slope. Minus 40 log 2.3 divided by 1 plus 0. That is equal to minus 40 log 2.3. That is equal to minus 40 log 2.3 equal to minus 14.5. Minus 14.5. Therefore, the coordinate here is minus 14.5. So after 10 decades, the slope is decreases at the rate of minus 80 dB. Here, here 20, 40, it decreases at the rate of minus 80. Therefore, 80 minus 14 is minus 94.5. The coordinates are minus 94, the 23, 94.5. Now we can draw the Bode plot. Before that, we have to find the phase angle. Phase angle. For that, we have to write the expression for angle of G of J omega. Expression for angle of G of J omega. What is the angle of G of J omega equal to, the first is J omega in the denominator, so minus 90 degree. Minus, because no real part. Then minus tan inverse of, for second term, for this tan inverse of omega minus tan inverse of, what is the imaginary part? 0.4 J omega. Tan inverse of 0.4 omega divided by 1 minus 0.2 omega square, real part. Imaginary part divided by 0.4 omega divided by 1 minus 0.2 omega square minus 180 degree, as omega tends to infinity. This is minus 90. This is minus 90. Therefore, when omega equal to infinity, it is 360. When omega equal to 0, minus 90. Therefore, angle varies from minus 90 to 360 degree. That's all. So we have to form the table and to find the angles. Omega, angle of G of J omega. First, 0.1, 1. Then corner frequency is 2.3 and 23. That's all. So when you substitute 0.1, the frequency, if you substitute 0.1, you got minus 98. Minus 98 degree. For 1, you are getting 162. Minus 162 degree. 2.3, you are getting minus 229. Minus 229. For 23, you are getting minus 351. Minus 351. For infinity, you will get 360 degree. Minus 360 or plus 360. Minus 360 degree. For that, you can draw both magnitude plot and phase plot. Yes, this is the magnitude plot for the given data. Yeah, for the table data. This is the phase plot. This is the phase plot for given for table data. Now we have to find the gain margin and phase margin. We have to draw a horizontal line at 180 degree. At 180 degree, draw a horizontal line. It cuts at A, and draw a vertical line at A This is what? Omega PC. This is 1. This is 2, 3, 4. Omega equal to 4 radians. Second is phase crossover frequency. Draw a vertical line. It cuts at B, the phase plot. The magnitude is minus 0.5 at B. Therefore, gain margin equal to minus of minus 5.5. That is equal to 5.5 dB. 5.5 dB gain margin. What is the phase margin? Phase margin equal to 180 plus phase angle 5. That is equal to, how to find that? Draw a horizontal line at 0 dB. It's cut at C. C is the frequency at C is called omega GC, gain crossover frequency. Draw a vertical line. You will get an angle. It cuts the phase plot at D. Draw a horizontal line at D. It gives minus 150. Therefore, 180 minus 150, that is equal to 30 degree. Both are positive. Therefore, stable system. First part is over. What is the first question? Using Bode plot, find gain margin, phase margin, gain crossover frequency and phase crossover frequency. The phase crossover frequency is here. The phase crossover frequency equal to 1.3 radians per second. Then gain crossover frequency also asked. Gain crossover frequency is point C. Point C is it cuts the here the frequency is 0.8. Therefore, gain crossover frequency is 0.8 radians per second. So all 4 answers we got for the first question. Now, what is the second question? Using Bode, how should the gain be adjusted so that the gain margin becomes 10 dB? So that the gain margin becomes 10 dB. What is the present gain margin? 5.5. What is the required gain margin? 10. But gain margin has to be increased. Now present is 5.5. If you subtract 5.5, 4.5 has to be, gain margin has to be increased. If you want to increase the gain margin, means we have to decrease the gain. Therefore, minus 4.5 is required. Minus 4.5 is 20 log K equal to minus 4.5. So from that you can find K. So the present required gain margin is 10. What is the present gain margin? Present gain margin is 5.5. Therefore, minus 4.5 is required. Gain required is minus 4.5. Therefore, 20 log K equal to minus 4.5. New gain is minus 4.5. 20 log K equal to minus 4.5. Therefore, this implies log K equal to minus 4.5 divided by 20. Therefore, K equal to 10 power minus 4.5 divided by 20. That is equal to 0.596. Question is, how should the gain be adjusted so that the gain crossover frequency is 1.2? What is omega at omega equal to 1.2 radians? What is the gain at that point that we have to see from the plot? At 1.2, what is the gain? At 1.2, this is 1.2. At 1.2, 5. This is the gain at 1.2. 1.2, what is the gain? This is 1.2 point. 1.2, the gain is 5. Gain is 5. Below 0, that's why minus 5. So the question is, the new gain crossover frequency must be 1.2. At 1.2, it should be 0 dB. At 1.2, it should be 0 dB for the new system. But here, the present case, we are having minus 5 dB. That minus 5 dB must be made 0. So minus 5 dB must be made 0 means we need 5 dB gain to make it 0 dB. So 20 log k equal to 5 dB. Therefore, this implies log k equal to 5 by 20 or k equal to 10 power 5 by 20. That is equal to 1.78, 1.778. The required phase margin is 45. The next question is, how should the gain be adjusted in the system so that phase margin is 45? The required phase margin equal to 45 degree. What is the present phase margin? Only 30. We need 45. 45 means what is the 5? This 30, how you got? 180 minus 150 equal to 30. This 150 is 5. Therefore, this 5 equal to 45 minus 180. That is equal to 135 degree minus 135 degree. 5 equal to minus 135. How we got this? We know that phase margin equal to 180 plus 5. Therefore, 5 equal to phase margin minus 180. Phase margin, given phase margin is 45 degree. So minus 180. Therefore, you are getting 135. At 135, what is the gain? We have to see. At 135, this is 135. This is 135. This is 135. At 135, what is the gain? If you see, it is at 135, it is 4 dB. At 135, it is 4 dB. At 135, 4 dB. This 4 dB must be 0. This 4 dB must be 0. So 20 log k equal to minus 4 dB, because 4 dB is there. You see that plus 4 dB. So it should be 0. Therefore, 20 log k equal to minus 4. So we have to give a minus 4 dB. Then only it will become 0. So 20 log k equal to minus 4. Therefore, log k equal to minus 4 divided by 20, or k equal to 10 power minus 4 by 20. Minus 4 by 20. That is equal to 0.63. Therefore, k equal to 0.63. What is the present phase margin? 30 degree. You have to increase the phase margin. That's why we have to decrease the gain. If you want to increase phase margin or increase gain margin, we have to decrease gain. From that, you can understand that it should be minus 4. But logically, what is the meaning of minus 4? At 135, at angle 135, because that is the required angle. What is the magnitude? The magnitude is 4. The magnitude is 4. 4 must be, we have to make 4 equal to 0. To make 4 equal to 0, the gain required is minus 4 dB. Therefore, minus 4. If you didn't understand the logic, what you can think is, to increase phase margin, we have to decrease the gain. So, minus 4. 20 log k equal to minus 4. Therefore, k equal to 0.63. Today, we have seen how to adjust gain for required gain margin, required phase margin, required gain crossover frequency. In the next class, we will see how to get the transfer function from Bode plot. That we will see in the next class. Yesterday we have learned how to draw Bode plot. Today we are going to learn how to find the transfer function from Bode plot. Transfer function from Bode plot. Directly let us solve on sum. For the Bode plot shown in figure, find the transfer function. Find the transfer function. This is the answer. This is the answer for given sum. How to find this transfer function from the, this is the answer. How to find the transfer function for a given Bode plot. We know that we will form a table to draw the Bode plot. We have to reverse the table. Reverse the table. The first step is there. Finally, we will write coordinate. Instead of that, here we will write the range. The range of frequencies. Then net slope. We are writing the reverse order. Then slope of slope by the factor. Then we have to write the corner frequency. We are writing in the reverse order. Then we have to write the factor. So this is the way by which we have to find. The range of frequency is, let us call, this is omega 1. Here, another corner frequency, that is omega 2. This is another corner frequency, omega 3. This is omega 4. That's all. This, here, the value is 0.1, it is given. At this corner frequency, omega 2 is not given, but the magnitude is given. In this corner frequency, the corner frequency is given 8 and the magnitude is not given. Here, the magnitude is given, but corner frequency is not given. For this, we have to find the transfer function. The first thing is, if it is a slope, negative slope, then that too its slope is minus 20 dB per decade, means it is K by S. If it is horizontal, means K only, that we know. If positive slope means with 20 dB per decade, means Ks. So these are all we know. So here 20 dB per decade, the slope is 20 dB per decade. The frequency range is from omega 1 to omega 2. The net slope is minus 20 dB per decade. dB per decade. This is also dB per decade. Minus 20. This is also slope by the factor is minus 20. No corner frequency. Initially, there is a slope. That's why it is K by 20 dB. That's why K by S. Minus 20 dB. That's why K by S. The next one is omega 2 to omega 3. Here, omega 2 to omega 3, the slope is minus 40 dB. Net slope is minus 40 dB. Earlier it is minus 20. Now it becomes minus 40, means the slope by the factor is minus 20. And it is minus 20. The corner frequency is omega 2. Corner frequency is omega 2. Therefore, T2 equal to tau 2 equal to 1 by omega 2. Therefore, the factor is negative slope with corner frequency. Therefore, 1 by T2s plus 1. So this is also over. The next one is omega 3 to omega 4. Omega 3 is here. It is given 8. The slope is changed from minus 40 to minus 20. The net slope is minus, in this range, minus 20. Earlier it is minus 40, now it becomes minus 20 means plus 20 dB. The corner frequency is omega 3. Therefore, T3 equal to 1 by omega 3. Therefore, this is numerator factor plus 20. Therefore, T3s plus 1. That is also. Now, omega 4 to infinity. So, what is the slope? Minus 40. So, it's changed from minus 20 to minus 40. It is changed from minus 20 to minus 40. Therefore, minus 20 is the slope given by the factor. Therefore, the corner frequency is omega 4. Corner frequency is omega 4. T4 equal to 1 by omega 4. Therefore, it is negative. That's why 1 by T4 is plus 1. That's the question is now reduced to finding K, finding T2, finding T3, and finding T4. That's all. If you find K, T2, T3, T4, we can form the transfer function. How to find K? At omega 2, we do not know the frequency, but here we know at omega 1, we know the frequency, but we do not know the magnitude. Here we do not know the magnitude. That's why it's not possible to find at 0.1. We do not know the magnitude. Magnitude we know at omega 2. That's why first we have to find the omega 2. First we have to find the omega 2. To find omega 2, what we can do is, for this what we will write is y2 equal to slope. This is the formula. Log omega 2 by omega 1 plus y1. This is the formula that we used to use. So if you use that formula, what is y2? Y2 is what is omega 1 and omega 2 we'll use, and here we do not know the magnitude. Here we do not know the magnitude. Here we do not know the frequency. Therefore, we know one straight line, but two unknown. That's why we cannot use that. That's why we cannot use that. But here, one more point is given. Here, one more point is given. The frequency is 0.4. No, see the diagram. The frequency is given as 4. At that point, what is the magnitude? Magnitude at this point is 0 dB. That is given. Therefore, instead of using this line, we can use this line. Line A is no use because two unknowns. Here magnitude is not known. Here frequency is not known. That's why we cannot use that line. But this line, here we know the magnitude 0, frequency is 4. Both points here we know. Here we know the magnitude, we do not know the frequency. That's why that we can find. So suppose this is omega 1, this is omega 1, this is omega 2, like that if you think. So y2 equal to 0. 0 equal to slope. What is the slope here of this line? Minus 40. Minus 40. Log omega 2 is 4. Omega 1 we do not know. 4 by omega 1. Omega 2. 4 by omega 2. 4 this point we know, but here the frequency is omega 2. Omega 2 plus y1. What is the magnitude here? 36. 36 that we know. Therefore, we can say that minus 36 divided by minus 40 equal to log 4 by omega 2, or 36 by 40 equal to 4 by omega 2. 4 by omega 2 equal to 4 divided by omega 2 equal to, this becomes positive because both negative, that's why it becomes positive. 4 by omega 2 equal to 10 to 4 by omega 2 equal to 10 to the power 36 by 40. If you use that 36 by 40, then omega 2 equal to 0.5. Omega 2 equal to, this implies omega 2 equal to 0.5. Therefore, we can substitute here omega 2 equal to 0.5. Omega 2 equal to 0.5 means T2 equal to 1 by 0.5 is 2. T2 equal to 2. Now, at omega 1, at omega 2, this is up to omega 2. This slope is up to omega 2. Now we know omega 2 is 0.5 and the magnitude also we know. Therefore, for this we can write 20 log k by omega 2. That is omega 2 is what? 0.5. 0.5 equal to 36. Therefore, k equal to, so what is k? From this k we can write k by 0.5 equal to 10 to the power 36 divided by 20. Therefore, k equal to 31.55. Therefore, k equal to 31.55. That's all. So we found two parameters. Now we have to find the third parameter, T3. Here, omega 3 we have to find. Omega 3 equal to what? For that, if you use omega 2, now we know both values. Omega 2 equal to what? Omega 2 equal to 0.5. Therefore, y2 equal to 36. Omega 3 equal to what? At omega 3, do you know magnitude? We do not know the magnitude. But omega 3 equal to 8 is given. 8 is given. Therefore, omega 3 equal to 8. Omega 3 equal to 8. Therefore, y3 equal to what? Y3 equal to what? Y3 is required. Omega 3 is equal to 8 means, omega 3 equal to 8 means T3 equal to 1 by 8. That is T3 equal to 0.125. 0.125. This also over. This also over. But we need y3 because to find omega 4 we need this value. We need this value. That's why let us find y3. Y3 is the old value. Therefore, what y2 we know all. Therefore, y3 equal to slope. What is the slope of this line? Minus 40 dB. Minus 40 log omega 3 is 8, omega 2 is 4, not 4.5. 0.5. Omega 2 is 0.5. 0.58 divided by 0.5 plus there the value is 36. If you use this, what we'll get? y3 equal to minus 12. Minus 12. y3 equal to minus 12. Minus 12. Now we know y3. y3 equal to minus 12. Therefore, here already we found this. Now we have to go for this range. We can go for this range. Omega 4 we have to find. The slope is minus 20 dB per decade. Here, the 8 comma minus 12 is the coordinate. Here, the coordinate is omega 4 comma minus 21. So omega 4 we have to find. Therefore, minus 21 equal to what is the slope? Slope is minus 20 log omega 4 not known. Omega 3 is 8 plus what is that slope? Magnitude is minus 12. So minus 21 minus 12 equal to minus 9. So minus 9 equal to minus 20 log omega 4 by 8. This implies minus minus getting cancelled. Therefore, 9 by 20 equal to log omega 4 divided by 8, or omega 4 by 8 equal to 10 to the power 9 by 20. This implies omega 4 equal to omega 4 equal to 22.55. Omega 4 equal to 22.55. So omega 4 equal to 22.55. Therefore, T4 equal to 1 by omega 4. T4 equal to 1 by 22.55 equal to 0.04. Therefore, T4 equal to 0.04. So we found all parameters. So we got the transfer function. What is K equal to 31.55? That is 31.55. Here T2 is the T3 is 0.125. That's why we got the numerator factor. Here this is 2. This is 0.044 and S in the denominator. Yes, we got all factors. This way we can find the transfer function. So we have to reverse the table. That's all. Yesterday we have learned how to draw Bode plot. Today we are going to learn how to find the transfer function from Bode plot. This is another example. Find the transfer function of the Bode plot shown in figure. Here G of S is given. This is the answer. Answer is this. We have to find this. So again, we have to form the table. Range, net slope, then slope, corner frequency, then factor. So these are all. Now range is first. This is this is omega 1. This is omega naught. Okay, let it be omega naught, omega 1, omega 2, omega 3, omega 4. Omega naught is 0.25. Omega naught and magnitude is 0.25. Here the range is omega naught to omega 1. Omega 1. What is the slope? The slope is 12 dB per octave. Already I told you that 6 dB per octave equal to 20 dB per decade. Here it is 12, therefore it is 40 dB. The slope is a positive slope, therefore 40 dB per decade. This is also dB per decade. 40 dB plus 40. Therefore, what is the net slope? Plus 40. What is corner frequency? No. Ks square. So 40, that's why Ks square. Numerator s square, because slope is positive. That's all. Then omega 1 to omega 2. Omega 1 to omega 2. In omega 1, omega naught is given 0.25. 0.25. And omega 1 also given 0.5. Omega 2 is given omega 2 is given 1. Omega 2 is given 1. Omega 3 also given. Omega 3 also given 2. Omega 1 is 1. Omega 3 is 2. Omega 2 is 1. Omega 1 is 0.5. Omega 1 is 0.5. So what is the slope? Slope is changed from 12 dB to 6 dB, reduced. That's why it is changed from 20 dB per decade. 12 dB means 40 dB per decade, which corresponds to what? 12 dB per decade. To how much reduced? 6 dB per decade. In other words, it reduced to 20 dB per decade. So it means what? Positive value reduced means some negative value came. So the new net slope is 20 dB per decade plus dB per decade. So it means what? There is a contribution by the factor is minus 20. That's why it reduced from minus 40 to 20. What is the corner frequency? The corner frequency is omega 1. Omega 1 equal to 0.5. Corner frequency is 0.5. Therefore, T1 equal to 1 by 0.5 equal to 2. The factor is negative, therefore 1 by 2s plus 1. 1 by 2s plus 1. So next one is from 2 to omega 3. Omega 3. Omega 2 to omega 3, it becomes 0. Net slope is 0. Net slope is 0. Already it is plus 20. It becomes 0 means the contribution is minus 20. Therefore, omega 2, the corner frequency equal to omega 2 equal to what? It is given in the diagram 1. Therefore, T2 equal to 1. T2 equal to 1. Therefore, the factor is minus, contribution is minus 20. Therefore, 1 by T2 is 1, S plus 1. The factor is S plus 1. Here, the factor is 1 by T1 S plus 1. Here, 1 by T2 S plus 1. T1 is 2, T2 is 1. So, next range is omega 3 to omega 4. Omega 3 to omega 3 to omega 4. Here, it reduced to minus 6 dB per active. Therefore, minus 0 to minus 6 dB. 6 dB means minus 20 dB. Therefore, the net becomes minus 20. 0 becomes minus 20 means the contribution is minus 20. Therefore, omega 3 equal to, it is given, that is 2. That is 2. Therefore, 1 by 2 equal to T3 equal to 1 by 2 equal to 0.5. Therefore, the factor is 1 by 0.5 S plus 1. 1 by 0.5 S plus 1. After that, no frequency response. That's why we cannot write anything. The only thing is we got this factor. We got this factor, this factor, this factor. So all the three factors we got. The only thing is we have to find K. To find K, either at omega naught or omega 1, we need the magnitude. At any one place, we need the magnitude. But magnitude is not given. But we can find the magnitude. At what is the 0.25 here, 0.5 here, 1. The slope is 6 dB per decade. So here 30 means it increases at the rate of 6 dB per decade, means here what is the value? 24 dB. 24 dB here. Here 0.5, here 0.25. 1 octave. This distance is 1 octave. 1 octave. 1 octave. 1 octave, it decreases at the rate of 6 dB per decade. Therefore, 30 minus 6, 24. Here 24. Here also 1 octave. 2 octave, 12 we have to subtract, therefore here 12 dB. So we know the values, from that we can find, let us use omega 1 to find K. 20 log modulus of K S square. That is equal to 20 log K omega square equal to 24, where omega equal to 0.5. Therefore, we will get 24 divided by 20 equal to log K multiplied by 0.5 square. 0.5 omega square. 0.5 square. Therefore, log K 0.5 square equal to K 0.5 whole square equal to 10 to the power 24 by 20. Therefore, K equal to 63.1. K equal to 63.1. K equal to 63.1. So that's all. So we got the value. So now we can combine all these things, we get the transfer function G of S equal to 63.1 S square upon 2S plus 1 S plus 1 0.5 S plus 1. Yes, we got the answer. Yesterday we have learned how to draw Bode plot. Today we are going to learn how to find the transfer function from Bode plot. Third sum. Suppose you are given an instrument, an amplifier, it may be an amplifier or some instrument. For that you are required to find the transfer function by experimental way. How we can find? We have to find the frequency response for this. This is the magnitude response. The table is given. Frequency omega equal to 0.1, 0.2, 0.3, etc. up to 35 is taken. For that, the magnitude in dB is given. The following frequency response test data were obtained for the forward path elements of a unity feedback control system. Plot the data on a semi-log paper and determine the transfer function of the forward path. So if you draw this on a semi-log sheet, it will be looking like this. The black is the magnitude plot. Now we need asymptotic plot, Bode plot. Asymptotic plot is required to find the transfer function. Therefore, we have to draw the asymptotes for this graph. If you draw an asymptote, this is the asymptote. This is the asymptote. This is the this dotted line is the asymptote. The slope of that asymptote is minus 20 dB per decade. And the corner frequency, again, draw the asymptote for this part. So the asymptote should pass through maximum part of the graph. Like that, you have to draw the tangent. That's all. So here, this covers the first asymptote covers asymptote plot covers this much area. Here also, this covers this much area. So if we draw a line, this is the asymptote. This is the asymptote. Second asymptote. Third asymptote, for this part, you have to draw a horizontal line. So now the plot becomes like this. The dotted line is the asymptotic plot. We know the corner frequency. The first asymptote and second, first asymptote plot and second asymptote plot meet at the 0.5, that is the corner frequency 1, omega 1. One corner frequency we got. What is the slope here? The slope of this line is minus 40 dB per decade. The change in slope is minus 20 dB. So now we'll here this minus 40 dB becomes 0. Here it becomes 0 dB. 0 dB per decade. That's all. Now we will form the we will find the transfer function. The transfer function is here. It is written. We know that it has one S because initial it is not horizontal. It is inclined at minus 20 dB. Therefore, K by S and one denominator first order factor because it has minus 20 dB slope here because of that. Here the change is 40 dB. Here the change is 40 dB. That's why there is a possibility of second order factor or repeated poles. We have to find whether it is second order factor or repeated poles. How to find that we'll see. Now we have to form the table to find the transfer function. The first range is omega naught to omega 1. This is omega naught to omega 1. Range is omega naught to omega 1. Omega naught is 0.1. 0.1 here. This is 0.5. Then net slope is given. That is minus 20 dB per decade. Slope is dB per decade. This is also dB per decade. Minus 20 dB. Again, this is minus 20 dB. Initially, they are slope. That's why corner frequency, no corner frequency. The factor is minus 20 dB. That's why K by S. We have to find the K. Factor is K by S. The next one is slope is changed from omega 1 to omega 2. Omega 2 is where? Here. This is omega 2. Omega 2 is 4.4. Omega 2 is 4.4 from 0.5 to 4.4. The slope is minus 40. The change is minus 20. Therefore, corner frequency is omega 1, that is 0.5. Omega 1 equal to 0.5. Therefore, T1 equal to 1 by 0.5, that is 2. The factor is negative slope. That's why 1 by T1 S plus 1, that is 1 by 2S plus 1. We got one factor. The next one is 4.4 to infinity. That is omega 2 to infinity. 4.4 to infinity. At 4.4 to infinity is 0. Therefore, it is contributed by the factor contributes plus 40. Then only it becomes 0 because earlier it is minus 40. Now it becomes 0 means plus 40. Therefore, omega 2 equal to 4.4 from the diagram. But 40 dB means there are two possibilities. It may be a repeated poles or second order factor. To find that here we see that the corner frequency is here. The corner frequency is here. True plot is here. This is black is the true plot. True plot. The gap is about 5 dB. 5 dB. Minus 5 dB. The gap is minus 5 dB. So asymptotic plot minus actual plot, you will give the error minus 5 dB. The error is negative. That's why it is over-damped system. That's why repeated factor. Over-damped or critically damped system. Damped part. It is not zeta value is not there. That's why it is repeated. That's why we can write 1 by T2. T2 equal to T2 square. 1 by T2 S plus 1 whole square. In the numerator, because plus 40. It is in the numerator. T2 S plus 1 whole square. T2 equal to 1 by T2 square equal to 1 by 4.4. Therefore, T2 equal to square root of 4.4. Square root of T4 equal to square root of 1 by 4.4. That is equal to 0.227. So 1 divided by 4.4. If we take square root of this equal to repeated poles 2.27. Omega 2 is 2.27. Yes. 1 by 1 divided by 4.4 equal to 0.227. Yes, repeated pole. It is not equal to 1 by 4.4. That is 1 by 4.4. That is equal to 0.227. Therefore, 0.227 S plus 1 whole square. Why repeated poles? Because the error is negative. More than about 6 dB. Error means it is repeated poles. That's all. Therefore, the transfer function is G of S equal to whether we got K not yet for me. So we cannot write. We have to find K. We got T1, T2. The only thing is we have to find K. To find K, we need two values. Here we know two values. Here, this is 30. This is 40 means 31, 32, 33. At omega naught, the magnitude is, at omega naught, magnitude is 33. So that can be used to find K. How we can find 20 log K by omega equal to 33. Therefore, log K by omega equal to 10 power 33 divided by 20. Omega equal to 0.1. Therefore, K by omega equal to 10 power 33 by 20. K by 0.1 equal to 33 by 20 equal to 33. So 10 power 33 divided by 20. Therefore, K equal to, this gives K value. K is equal to 4.5. K equal to 4.5. 4.5. So K also we know that is equal to 4.5 divided by S. So we got the transfer function. This is the first slope. That's why 1 by S. If first is horizontal line means K only. This is K by S. K by S. If positive slope means Ks. You extend that first slope till it intersects 0 dB line. This is the 0 dB line. This is the 0 dB line. The first slope is extended. Extend first slope till it intersects with the 0 dB line, x-axis. It intersects at 4.5. So we can find that way also K equal to 4.5. That way also you can find K. Therefore, the transfer function is 4.5, that is K divided by S, and numerator we have 0.227. 0.227. S 227 S plus 1 whole square divided by 2S plus 1, 2S plus 1 multiplied by 2S plus 1. That's all. That's all. Yes. We got the same answer. Therefore, the given transfer function is this. This is the given. This is the transfer function for the given Bode plot. Frequency response. So, how to find? Draw the frequency response, then make it a asymptotic plot, approximate plot by drawing tangents so that it covers most of the points. We got 3 segments. For the 3 segments, we got 3 components. That's all. Another example. Here also frequency response is given. Frequency response is given. Frequency response is given. For that, this is the answer for that frequency response. Here we have drawn that this dark line is the magnitude plot. Magnitude plot. Then we are drawing the asymptotes. The first slope extended till intersects with the 0 dB line, so that we can find it directly K, that is K equal to 200. K equal to 200. The slope here is minus 20 dB per decade. Initial slope, not horizontal line, therefore K by S. The first factor is K by S. The next one is it becomes horizontal. It becomes horizontal. The corner frequency is 1.9. The corner frequency omega 1 equal to 0.9. The slope becomes minus 20 to 0. Therefore, numerator factor. Therefore, omega 1 equal to 0.9 means 1 by 0.9. 1 by numerator factor 1 by 0.9. S plus 1. Why numerator factor? Minus 20 becomes 0. This becomes 0 dB per decade. This is second factor. This is first factor, second factor, numerator factor. Then third factor. Third factor, again, it becomes minus 20 dB. 0 becomes minus 20 dB. Corner frequency is 9. 9. Therefore, 1 divided by 1 by 9. S plus 1. So that is third factor. Then fourth factor, here minus 40 dB. Minus 20 becomes minus 20 means another first order factor. The corner frequency is 110. Therefore, 1 by 110 S plus 1. That's all. So 1 by 0.9, 1 by 9, 1 by 110 S plus 1. These are the factors. Then 1 by 0.9 is 1.11. 1 by 0.9 is 0.111. 1 by 110 is 0.009. So we got the transfer function.